Right now, you are standing on a tiny rock, hurtling through the sky at about 800,000 kilometers per hour. Around you, roughly 200 billion galaxies drift through the vastness of space. Each galaxy holds hundreds of billions of stars, and each star may have its own planets. The numbers are so enormous that the human brain can barely grasp them. And yet, the strangest thing is not how many stars are out there. It is the fact that we can see only about 5% of what actually exists. The remaining 95%, completely missing from view. Not because it is too far away, but because it is invisible. It emits no light, reflects no light, and barely interacts with anything we can measure. So what is it? Why does it exist? The answer remains a mystery. And that is just one of hundreds of questions that keep scientists awake at night. There is an even bigger one, deeper and more unsettling. What was there before the universe began? Everything has a beginning, right? A house is built one day, a tree sprouts from a seed, even you have a birthday. So the universe should be no different. But what created that beginning? What started the start? Tonight, we are setting out together to search for answers to the greatest questions humanity has ever asked about the universe. What existed before the Big Bang? How did something emerge from nothing? Where did 95% of the universe go? Does the universe have a center? Does it have an edge? What does the true shape of the universe look like? Are we alone in this vast cosmos? And one day, how will it all end? These are not easy questions. Even the smartest scientists in the world are still debating, still searching for evidence, still trying to decode the answers. And what they have uncovered so far? They are stranger, crazier, and more awe-inspiring than anything you might imagine. Are you ready? Because this journey is about to blow your mind. Everything has to start somewhere, right? So, where did the universe begin? With a point smaller than an atom. Smaller than a speck of dust. So small that even the most powerful microscope on Earth could never see it. And yet, that tiny point contained the entire universe. Every galaxy, every star, every planet, every living thing, you, me, all of it, packed tightly inside. At this strange point, time stopped flowing, space ceased to exist, and every known law of physics fell apart. Scientists call it a singularity. This was the state of the universe before the Big Bang. According to the Big Bang theory, about 13.8 billion years ago, the universe began as an incredibly small, incredibly hot, incredibly dense point. Then, in a flash, it expanded violently at a speed beyond imagination. From that moment on, the universe kept stretching, cooling, and growing, and it is still expanding today. But this singularity is unlike anything we have ever encountered. Its density is infinite, meaning the entire mass of the universe was compressed into a point with zero size. That sounds insane, doesn't it? How can something infinite exist in the real world? This is exactly why scientists say that at a singularity, space and time lose all meaning. Every equation breaks down. Every law of physics stops working. To understand how time itself can stop, we need to go back to Albert Einstein, one of the greatest minds in history. He discovered something extraordinary: time is not constant. It can speed up or slow down, depending on the mass around it. More specifically, Einstein's theory of relativity tells us that large amounts of mass warp space and slow time down. The Earth weighs about 6 sextillion tons, and that enormous mass bends space like a bowling ball placed on a stretched sheet of fabric. That bend is what we feel as gravity. But it does more than that, it also makes time run just a tiny bit slower compared to places with weaker gravity. It sounds like science fiction, but it is real, and it has been proven. In 1959, two American scientists, Robert Pound and Glenn Rebka, carried out a simple yet crucial experiment. They placed one atomic clock on the ground and an identical one at a height of 22.5 meters. Then they compared how fast the two clocks were ticking. The result was astonishing. The clock higher up ran slightly faster than the one on the ground. The difference was incredibly small, just a few trillionths of a second, but it was enough to prove Einstein right. Gravity is slightly stronger at ground level than at 22.5 meters up, so time down below runs more slowly. This was not an illusion, not a faulty clock, it was the true nature of the universe. Now apply this idea to the singularity. All the mass of the universe squeezed into an unimaginably tiny point. The mass is infinite. According to Einstein, the greater the mass, the slower time flows. So what does infinite mass do? It brings time to a complete stop. Time no longer flows. There is no past, no future, not even a present. This is why Einstein argued that the question, what came before the Big Bang, is meaningless. The word before assumes that time already exists. But time itself began with the Big Bang. Before that, there was no time. No before. It is like asking, what is north of the North Pole? The question has no answer, because nothing exists north of the North Pole. In the same way, there is no before the Big Bang, because time did not yet exist. This is hard to accept. Our brains are wired to think in terms of before and after, cause and effect. But the universe does not have to follow what feels logical to us. It plays by its own rules. Still, the idea that nothing existed before the singularity makes many people uncomfortable. It completely erases the concept of a past. It suggests that the universe appeared out of nothing, with no reason, no cause. That clashes with our intuition. We want to know why. We want explanations. Even so, most scientists accept the Big Bang theory, because the evidence for it is overwhelming. The universe is expanding, and we can see this through telescopes. Galaxies are moving away from us, like dots of ink on the surface of a balloon as it is inflated. The farther away they are, the faster they recede. This tells us that in the past, everything was closer together, smaller, denser. The second key piece of evidence is the cosmic microwave background radiation. This is the oldest light in the universe, created about 379,000 years after the Big Bang. It fills all of space like an invisible fog, carrying information from the universe's earliest moments. Scientists detected it with radio telescopes and studied it in detail to peer deep into the cosmic past. All of this evidence points to one conclusion: the universe had a beginning. A moment when everything started. Before that? Perhaps there truly was nothing, in the most literal sense. No space to stand in, no time to pass, no matter to exist. But the story does not end here. There is a gap in this theory. The Big Bang explains the universe after the bang, but not the bang itself. What set it off? Why did the singularity explode? How does nothing turn into everything? This is the biggest and hardest question of all. That is why scientists keep searching. They build massive particle accelerators, launch powerful telescopes into space, and write thousands of complex equations. All of it in the hope of finding even the smallest clue about the universe's first moments. Did the Big Bang really happen? Is there definitive proof? Or is it all just a beautiful theory written on paper? Beautiful theories are easy to come by, but science does not run on elegant ideas alone. Science demands evidence. It demands things we can see, measure, and test again and again. So does the Big Bang have evidence? The answer is yes, a lot of it. The first piece of evidence is right in front of us every night when we look up at the sky. In 1929, an astronomer named Edwin Hubble discovered something strange. Every galaxy was moving away from us. Not just a few, but all of them. And the farther away a galaxy was, the faster it was receding. He measured this by studying the light coming from those galaxies. Light from an object moving away gets stretched, shifting toward the red end of the spectrum. It is similar to how an ambulance siren sounds lower in pitch as it speeds away from you. This effect is called redshift. This discovery was shocking, because it pointed to one unavoidable conclusion. The universe is expanding. Galaxies are not simply flying through space. Space itself is stretching. Imagine drawing dots on the surface of a balloon and then blowing it up. The dots do not move across the surface, yet they all drift farther apart because the surface itself is expanding. What does that mean? It means that in the past, the universe was smaller. The farther back you go in time, the smaller it becomes. Rewind the cosmic movie far enough, and everything collapses into an unimaginably tiny point. That point is called a singularity, the starting line of the Big Bang. This is the first direct piece of evidence that the Big Bang is not just a story. The second piece of evidence is even stronger. It is the cosmic microwave background, usually called the CMB. Scientists often describe it as the oldest light ever discovered. It is a faint afterglow from the early universe, a kind of living fossil from a very distant past. The story begins in 1964. Two engineers, Arno Penzias and Robert Wilson, were working with a massive radio antenna in New Jersey. They kept hearing a strange noise, a persistent hiss that seemed to come from nowhere. They tried everything to get rid of it. They cleaned the antenna, chased out pigeons nesting inside, checked every cable and component. But the noise never went away. It was steady, faint, and coming from every direction in the sky. Eventually, they realized this was not interference. It was a real signal from the universe itself. A sea of microwave radiation filling all of space, arriving equally from every direction. Its temperature was about -270 degrees Celsius, far colder than ice, yet just slightly warmer than absolute zero. This was the echo of the Big Bang. This radiation formed about 13.8 billion years ago, specifically 379,000 years after the Big Bang. Why such a precise moment? Before that time, the universe was too hot and too dense. Light could not travel freely, constantly scattering off charged particles. The universe was opaque, like a thick cosmic fog. But after 379,000 years, it cooled enough for the first atoms to form. Light was finally able to move unhindered. Those photons traveled for 13.8 billion years, stretched along with the expanding universe, cooled down into microwaves, and eventually reached us today. Discovering this background radiation was like finding the oldest photograph of the universe. It contains information about the earliest moments, about how the universe evolved, and about its original structure. Scientists have launched multiple satellites just to study it. They mapped its temperature across the entire sky, revealing tiny hot and cold spots. These small fluctuations became the seeds of future galaxies. Using this evidence, scientists reconstructed the story of the universe's first moments. They divide it into 7 stages, or 7 cosmic eras. Each one lasted an incredibly short time, yet each played a crucial role. The first is called the Planck era. It spans from 0 to 10 to the -43 seconds after the Big Bang. That number is so small you would need to write 42 zeros after the decimal point before reaching a 1. During this moment, the universe was smaller than a proton. Temperatures and densities were so extreme that our known laws of physics no longer apply. We do not truly know what happened then. Next comes the Grand Unification era. The universe was still incredibly hot and tiny, but it had begun to cool slightly. The fundamental forces of nature started to separate. At first, all forces were one. As the universe expanded and cooled, they split into gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. It is a bit like ice melting into liquid water as the temperature changes. Then came the inflationary era, the most mind-bending phase of all. In a fraction of a second, shorter than a blink, the universe expanded at an unimaginable rate. It grew millions of times larger in less than a second. Space itself expanded faster than the speed of light. That sounds like a violation of physics, but it is not, because nothing was moving through space. Space itself was stretching. After that came the electroweak era. During this time, electromagnetism and the weak nuclear force were still unified. Temperatures remained so high that particles could not settle into stable combinations. Everything existed as a seething, superheated soup. As the universe cooled further, it entered the quark era. Quarks began to exist freely. These tiny building blocks would later form larger particles like protons and neutrons, but for now they moved independently. Then came the hadron era, when quarks finally bonded together to form protons and neutrons. These particles would later become the cores of atoms. The universe was still extremely hot, but structure was beginning to emerge. Finally came the era of hydrogen recombination. After 379,000 years, the universe cooled enough for electrons to orbit atomic nuclei, forming the first atoms. Mostly hydrogen, with a little helium. Light could finally travel freely. The universe went from opaque to transparent. This moment produced the cosmic background radiation we detect today. All of these stages unfolded within the first few 100,000 years. But by then, the foundation of the universe was in place. The laws of physics had stabilized. Fundamental particles existed. Space expanded smoothly. From this point on, the universe would continue to evolve, forming stars, galaxies, planets, and eventually life. Every part of this story has been calculated, simulated, and tested against observations. The Big Bang is no longer just a hypothesis. It is the most well-supported theory we have for the origin of the universe. And yet, the story gets even stranger. Because when we zoom into the smallest scales, into the realm of fundamental particles, reality becomes far more bizarre than anything we have talked about so far. In the quantum world, everything you think you know about reality is wrong. Completely wrong. The rules you learned in school, your everyday experiences, none of them apply anymore. A particle can exist in two places at once. An object can pass straight through a wall. You can never know the exact position of something. Even more strangely, simply observing it changes it. Sounds crazy? That is exactly what the extremely tiny world is like, the world of particles smaller than atoms. When Stephen Hawking, one of the greatest minds of the 20th century, looked back at the early universe, he realized something crucial. That scale was unimaginably small, smaller than atoms, smaller than protons themselves. At that size, the familiar laws of physics stop working. Quantum mechanics takes over. Hawking went on to develop an entirely new field called quantum cosmology, applying the bizarre rules of the quantum world to the universe as a whole. One of the most important conclusions was this: we cannot pinpoint the exact moment the universe was born. Not because we lack technology or data, but because the nature of a quantum universe does not allow it. Just as you cannot know the exact position of a particle, you cannot know the precise beginning of the universe. Time itself becomes fuzzy, blurred, uncertain. This idea is tied to a famous principle discovered by Werner Heisenberg. His uncertainty principle says there are pairs of quantities you can never measure precisely at the same time. For example, you cannot know both the exact position and the exact speed of a particle. The more precisely you measure one, the less clear the other becomes. This is not a flaw in our instruments, it is a hard limit built into nature itself. When we apply this to the universe, the result is deeply strange. In the quantum world, nothing is ever truly certain. Everything is described by probabilities. A particle does not sit in one definite location, it exists in many places at once, each with a certain probability. Only when you measure it does it finally choose a position. In the same way, the early universe did not have a single, well-defined state. It fluctuated, hazy and uncertain, like a cloud of probabilities. This leads to an even more shocking realization: a vacuum is not truly empty. In the classical world we are used to, a vacuum means nothing at all, no air, no dust, absolute emptiness. But in the quantum world, a vacuum is noisy and restless. Why? Because of Heisenberg's uncertainty principle. According to it, you cannot have a region of space that is perfectly calm, perfectly empty. Complete nothingness would mean energy is exactly zero, with no fluctuations at all. But knowing energy with perfect precision would violate the uncertainty principle. So even in a vacuum, energy must constantly fluctuate up and down. These fluctuations are not just theoretical. They can create real particles. For an incredibly brief moment, two particles can appear out of nothing, one particle of matter and one of antimatter. They exist for a split second, then collide, annihilate each other, and vanish as if they were never there. This happens everywhere, all the time, throughout space, creating an invisible quantum foam. Scientists have actually confirmed this effect. They performed experiments with two metal plates placed extremely close together in a vacuum. Theory predicts that fewer virtual particles can exist between the plates than outside, because the space is restricted. This difference creates a tiny pressure that pushes the plates toward each other. That force has been measured. It is unbelievably small, but it is real. The vacuum is truly not empty. Now think about this. The universe began from an incredibly tiny point. At that scale, quantum mechanics rules everything. The quantum vacuum fluctuates violently, constantly creating and destroying particles. So could the entire universe itself be a gigantic quantum fluctuation? Could the Big Bang have been a lucky fluctuation, where a pair of particles appeared but failed to annihilate, expanding too quickly and becoming our universe? It sounds unbelievable, but this is one of the serious hypotheses scientists are actively studying. They call it the birth of the universe from a quantum nothing. Not nothing in the philosophical sense, but nothing in the physical sense, a lowest energy state that still contains quantum fluctuations. Stephen Hawking, together with James Hartle, developed a mathematical model for this idea. They proposed that the universe has no clear boundary in time. Instead of a sharp beginning, time in the distant past becomes more like space. Think of the surface of the Earth. It has no starting point, no corner, no edge. You can travel around it forever without ever finding a beginning or an end. In this model, the universe is similar. Here, the question, what came before the Big Bang, becomes meaningless in a different way. Not because time does not exist, but because time curves into a closed shape. There is no before, just as there is no place north of the North Pole. This approach is very different from Einstein's, but it neatly avoids the hardest questions about origins. Of course, all of this is still theoretical. We cannot travel back in time to check. We cannot create a miniature Big Bang in a laboratory and watch what happens. But these theories help us explore the possibilities, the ways the universe could have come into existence. What makes this especially remarkable is that quantum mechanics, strange as it is, has been tested millions of times in experiments. Every one of its predictions has been confirmed with astonishing precision. The computer you are using, the phone in your pocket, all of it works because quantum mechanics is correct. So when we apply it to the early universe, we have good reason to trust it there as well. Another fascinating idea is that in the quantum world, nothing is not a stable state. The quantum vacuum is always trying to produce something. It cannot remain quiet. Fluctuation is its natural state. So instead of asking, why is there something rather than nothing, a better question might be, why wouldn't there be something? Because according to quantum mechanics, fluctuation and particle creation are the most natural conditions of all. Of course, there is still a huge gap between a few tiny particles and a universe filled with hundreds of billions of galaxies. That is why we need additional mechanisms, like the period of cosmic inflation we discussed earlier. But the core idea remains, quantum mechanics allows something to emerge from almost nothing. No miracles required. No laws of physics broken. Just the natural fluctuations of the quantum vacuum. At first glance, this can feel like a loophole, like saying, yes, there is something, but it's so small it doesn't count. But that is exactly the point. In physics, nothing does not mean the same thing it does in everyday language. Physics talks about the lowest possible energy state, not the absolute absence of everything. And even that lowest energy state still contains potential, still fluctuates, and can still give rise to a universe. So we have traveled from the classical Big Bang, through Einstein's relativity, to Hawking's quantum universe. Each step gives us a deeper, stranger view of cosmic origins. And all of them circle around the same central question, the biggest, hardest, and most mind-bending question of all: how does something come from nothing? Look up at the night sky and you see stars sparkling. Each one is a gigantic sun, heated to millions of degrees. These stars gather into galaxies, vast spirals of light holding hundreds of billions of stars. In the entire observable universe, there are about 200 billion galaxies like that. Each galaxy contains countless planets, moons, and asteroids. Added together, the number of stars in the sky is greater than the number of grains of sand on all the beaches of Earth. There is even life. At least here on Earth, we know for sure that life exists. From tiny bacteria to massive whales, from plants to humans. Millions of species are alive right now. All of them are made of matter, built from atoms of carbon, hydrogen, oxygen, and nitrogen. These atoms were forged in the hearts of stars, blasted into space when stars died, and later came together to form planets and, eventually, life. So how could all of this wonder come from nothing? The answer lies in a set of very special conditions, conditions that had to be precise down to the smallest detail. The first condition is the existence of ordinary matter. This is the kind of matter we see and touch every day. It makes up stars, planets, and people. Ordinary matter accounts for about 5% of the total content of the universe. That may sound small, but it is the only part that shines, the only part we can directly see. The second condition is dark matter. This stuff is invisible. It does not emit light, absorb light, or reflect light. We know it exists because it has gravity. Galaxies spin so fast that they should tear themselves apart, yet they remain intact. The only explanation is that there must be extra, invisible mass holding them together. Dark matter makes up about 25% of the universe. The third condition is even more mysterious: dark energy. This is not matter at all, but a strange form of energy that fills space itself. It pushes the universe to expand faster and faster. The more space there is, the more dark energy there is, and the stronger the push becomes. This is the largest component of all, accounting for about 70% of the universe. The fourth condition is the presence of tiny fluctuations in the early universe. The newborn universe was not perfectly uniform. Some regions were slightly denser, others slightly emptier. These differences were incredibly small, about 1 part in 100,000. Yet these tiny ripples are what created structure. Denser regions pulled in surrounding matter, grew over time, and eventually became galaxies. Without these initial fluctuations, the universe would be a smooth, featureless cloud with no stars, no planets, and no life. The fifth condition is that the laws of physics must be stable. Gravity, electromagnetism, and the nuclear forces must have exactly the right strengths. Change them by just 1% and the universe collapses. Stars would never form. Atoms would be unstable. Life would be impossible. Our universe is remarkably lucky that these constants fall within the narrow range that allows life to exist. So again, how did all of this arise from nothing? The key lies in the most famous equation in science, E equals mc squared. Einstein's equation tells us that energy can turn into matter and matter can turn into energy. They are simply two forms of the same thing. In the universe, if you add up all matter, all light, and all energy, you get an enormous amount. This is positive energy. But there is also a kind of negative energy, gravity. When two objects attract each other, gravitational energy is negative. The closer they get, the more negative it becomes. The remarkable idea is that the total positive energy of matter and the total negative energy of gravity can cancel each other out. Scientists have done the math very carefully. They add up all the energy in the universe, energy from stars, from galaxies, from radiation, from dark matter, and from dark energy. Then they subtract the negative energy of gravity. The result is almost zero. The total energy of the entire universe is approximately zero. That sounds strange, but it explains a lot. It means the universe could come from nothing without violating the law of energy conservation. The total energy before was zero, and the total energy after is still zero. Nothing was created, nothing was destroyed. Positive energy, matter, simply separated from negative energy, gravity. Think of it like debt. You borrow 1 million from a bank. Now you have 1 million in cash, which is positive, but you also owe 1 million, which is negative. Your net worth is still zero. In the same way, the universe borrows energy from gravity to create matter. The total remains zero, so no laws are broken. This allows the universe to create itself without any external energy source. No one has to pump energy in. No miracles are required. All it takes is an initial quantum fluctuation, and then everything unfolds according to the laws of physics. This process happens during the phase we call inflation. In an incredibly short moment, space expands wildly. The energy of the inflation field turns into matter and radiation. At the same time, gravity generates an equal amount of negative energy. The total stays zero, but now there is something instead of nothing. Another way to picture this is splitting water into hydrogen and oxygen. A water molecule just sits there doing nothing. Add energy, and it splits into two gases. Before, there was one thing. After, there are two. But the total number of atoms is unchanged. Similarly, the universe splits nothingness into positive matter and negative gravity. Of course, this only explains the physics. It does not explain why the laws of physics exist at all. Why is there quantum mechanics? Why is there gravity? Why do the constants have exactly these values? Those questions are beyond the reach of current science. Maybe we will answer them one day, or maybe they mark the ultimate limits of human understanding. What matters is that we now understand how the universe could create itself without breaking any physical laws. No miracles, no gods required, just math and physics. From a state of zero total energy, through quantum fluctuations and inflation, the universe made itself. But there is still one huge problem we have not mentioned. According to theory, the Big Bang should have created matter and antimatter in equal amounts. When matter and antimatter meet, they annihilate each other and turn into light. The universe should have ended up filled only with light, with no matter left. Yet look around. Everything is matter. Stars, planets, people, all made of matter. Antimatter has almost completely vanished. Why? Why does the universe contain matter, but almost no antimatter at all? In theory, you shouldn't exist. None of us should. Earth shouldn't exist. The sun, the stars, the galaxies, none of them should be here. Instead, the universe should have been nothing more than an empty ocean of light, with no matter at all. And yet, here we are. This is one of the greatest mysteries that science still hasn't fully solved. The story begins with symmetry in physics. For every type of particle of matter, there exists a mirror counterpart called antimatter. Electrons have anti-electrons. Protons have antiprotons. Neutrons have antineutrons. Antimatter particles are identical to their normal counterparts in every way except one: they carry the opposite electric charge. Electrons are negatively charged, anti-electrons are positively charged. In all other respects, they are the same. Something strange happens when matter meets antimatter. They annihilate each other in a flash of light. All of their mass is converted into pure energy, into gamma rays, into light. Nothing is left behind. This process is called annihilation, and it releases an enormous amount of energy. exactly as predicted by Einstein's equation, E equals m times c squared. Now rewind to the Big Bang. According to every law of physics we know, when energy turns into matter, it must create matter and antimatter in equal amounts. If a proton appears, an antiproton must appear as well. If an electron is born, so is an anti-electron. This is a fundamental symmetry of nature, a conservation rule written into the fabric of reality. That means in the first moments after the Big Bang, the universe should have been filled with both matter and antimatter. They would have been flying around everywhere, constantly colliding. Each collision would end in annihilation, turning pairs into light. Within seconds, all matter and antimatter should have wiped each other out completely, leaving behind only radiation. But that didn't happen. Look around. The universe is full of matter. Earth is made of matter. Your body is made of matter. The sun, the stars, everything we see is matter. Antimatter, on the other hand, is almost nowhere to be found. Scientists have to work incredibly hard just to create tiny amounts of it in particle accelerators. In nature, antimatter is extraordinarily rare. The numbers make this even more astonishing. Calculations show that for every 1 billion matter-antimatter pairs that annihilated each other, exactly one particle of matter survived. That's a ratio of 1 billion plus 1 to 1 billion. This minuscule imbalance, just 0.0000001%, created the entire universe as we know it. All the galaxies, all the stars, everything we can see, all of it comes from that tiny leftover. So the question is obvious. Why was there an imbalance at all? Why not a perfect 50-50 split? What tipped the scales? According to symmetry, this should not have happened. And yet, it did. Something must have broken the symmetry. Scientists call the process that created this imbalance baryogenesis. Baryons are particles like protons and neutrons, the building blocks of atomic nuclei. Baryogenesis is the mechanism by which the universe ended up producing slightly more baryons than antibaryons. There are several ideas trying to explain how this could have happened. One of the most famous involves something called CP violation. CP stands for charge and parity. Put simply, it's a rule that says the laws of physics should be the same for matter and antimatter. But experiments have shown that in rare cases, this rule is broken. Matter and antimatter do not behave in exactly the same way. The effect is tiny and only shows up in very specific interactions. But in the early universe, when temperatures were unimaginably high and energies were extreme, these interactions could have happened much more often. Slowly, over time, they could have built up a small imbalance between matter and antimatter. Then, as the universe cooled, most of it annihilated away, leaving behind that tiny excess of matter. Another hypothesis involves heavy particles that we haven't discovered yet. In the early universe, there may have existed extremely massive, high-energy particles. They were unstable and quickly decayed. When they did, they may have produced slightly more matter than antimatter. The particles themselves vanished, but their legacy remained, a universe biased toward matter. There's also a more radical idea. Perhaps the universe did create matter and antimatter in equal amounts, but they separated into different regions. One region filled with matter, another filled with antimatter. We happen to live in the matter region. Somewhere far away, there could be antimatter galaxies. But this idea has serious problems. If there were boundaries between these regions, we would see intense flashes of light from ongoing annihilations. And we don't observe anything like that. The truth is, we still don't know exactly what happened. We know symmetry had to be broken. We know it must have happened extremely early, within the first second after the Big Bang. We know the effect was tiny, but absolutely crucial. The exact mechanism, however, remains a mystery. Scientists are actively searching for answers. They run experiments at the largest particle accelerators on Earth, smashing particles together at enormous energies to recreate conditions similar to the early universe. They look for new symmetry violations. They hope to uncover clues about how baryogenesis really works. What's remarkable is that this microscopic imbalance created everything. Just 0.0000001% more matter was enough to give us a universe full of stars, planets, and life. Without it, the universe would be an empty sea of light, no structure, no complexity, no awareness. Our existence rests on an almost impossibly small difference. Some people see this as evidence of intelligent design. They argue that only a higher power could fine-tune the universe so precisely. Scientists, however, don't accept that explanation. They believe there must be a physical mechanism, a natural reason. We just haven't found it yet. Perhaps in the future, with a deeper understanding of high-energy physics, fundamental particles, and unified theories, we will solve this mystery. Maybe we'll discover that the imbalance wasn't random at all, but an inevitable consequence of a deeper law of nature. For now, it remains one of the biggest unanswered questions in science. Why do we exist? Why is there matter at all? Why didn't everything turn into light from the very beginning? The answer lies somewhere in the first moments of the universe, under extreme conditions that we are only just beginning to understand. Ordinary matter is already strange enough. But it makes up only about 5% of the universe. What about the other 95%? For that, you'll have to wait until we talk about dark matter. Dark matter is the strangest thing in the universe. It does not emit light, absorb light, or reflect light. You cannot see it. You cannot touch it. It is passing through you right now without you ever noticing. And yet, it makes up about 25% of the total mass of the universe, 5 times more than ordinary matter. Without dark matter, galaxies would fly apart, and the universe would look nothing like it does today. The strangest part? We do not know what it is. Scientists have compiled a list of fundamental particles called the Standard Model. It includes electrons, protons, neutrons, quarks, photons, and many others. Everything we can see, touch, and measure is made from particles on that list. But dark matter is not on it. It is something entirely different, something the Standard Model does not predict. So what could it be? Scientists have proposed several candidates. Each one comes with its own logic and its own evidence, but none has been confirmed. The first candidate has a long name, weakly interacting massive particles. These are hypothetical particles, much heavier than protons, possibly hundreds of times heavier. But they barely interact with ordinary matter at all. Trillions of weakly interacting massive particles could be passing through your body every second without hitting anything. Once in a very long while, one might collide with an atom in your body, but the chance is incredibly small and completely harmless. Scientists are trying to catch these rare collisions. They build enormous detectors deep underground, far from the noise of cosmic rays. They fill massive tanks with ultra-sensitive liquids and wait. They wait for a weakly interacting massive particle to strike and produce a tiny flash of light. They have waited for years, recording millions of events, and still there is no convincing evidence. It could be that these particles exist but are rarer than expected. Or it could be that they are simply not the answer. The second candidate is the axion. This is an extremely light particle, billions of times lighter than an electron. It was originally proposed to solve a different problem in particle physics, but later scientists realized it could also be dark matter. Axions almost never interact with anything. They could have been produced in enormous numbers in the early universe. Each one is incredibly light, but together they could still account for 25% of the universe's mass. The problem with axions is that they are incredibly hard to detect. Experiments try to catch them using powerful magnetic fields. The idea is that an axion might turn into a photon, a particle of light, as it passes through the field. But the signal is unbelievably weak. It is like searching for a needle in a haystack where the needle is smaller than an atom. The third candidate is the sterile neutrino. Ordinary neutrinos are extremely light particles that pass through almost everything. Every second, trillions of neutrinos from the sun stream through your body. Sterile neutrinos are a heavier version, possibly millions of times more massive. They do not interact through the weak nuclear force like ordinary neutrinos. They interact only through gravity. That makes them completely invisible except for their mass. Theoretical physicists like sterile neutrinos because they help explain why ordinary neutrinos are so light. According to theory, there should be both light neutrinos and heavy sterile ones. It is a kind of elegant mathematical balance. But no one has ever detected a sterile neutrino. For now, it remains a hypothesis. The fourth candidate is even stranger: super-heavy particles created by gravity itself. In the early universe, when energies were unimaginably high, gravity may have been strong enough to produce particles on its own. No collisions required, no external energy source, just the curvature of spacetime. These particles could be extraordinarily massive, heavier than any particle we have ever observed. Very few would be created, but because each one is so heavy, their total mass could still be enough to make up dark matter. This idea is difficult to test because these particles would have been created when the universe was only about 1 second old. We cannot recreate those conditions in a laboratory. All we can do is calculate, predict, and search for indirect clues. All of these candidates share one thing in common. They must have been created in the early universe. But where did the energy to create them come from? That is the core question. Ordinary matter was created from the energy of the Big Bang, when light turned into particles. But dark matter, how did it appear? One possibility is that dark matter was created at the same time as ordinary matter, in the first moments after the Big Bang. As energy turned into particles, it produced not only electrons and protons, but also dark matter particles. Ordinary matter then interacted, combined, and formed atoms, molecules, stars, and planets. Dark matter did not. It drifted freely, never clumping together, interacting only through gravity. Another possibility is that dark matter was created during inflation. This was an incredibly brief period when the universe expanded at a ridiculous rate. The energy of the inflation field could have transformed into many kinds of particles, not just ordinary matter. It is possible that much of that energy became dark matter. When inflation ended, those particles remained, forming invisible halos around galaxies. There is also a more radical possibility. Dark matter might not be a particle at all, but a completely different form of energy. It could be connected to extra dimensions of space that we cannot see. It might be a sign of a deeper theory that we have not yet discovered. Some physicists believe that understanding dark matter will trigger a revolution in how we understand the universe. But for now, these are all just ideas. The truth is, we still do not know what dark matter is, where it came from, or how it was created. We only know that it must exist, because without it, galaxies could not form and the universe would be unrecognizable. Maybe in the coming years, experiments will detect a new particle, some long-awaited signal. Maybe we will finally solve this mystery. Or maybe the answer is far deeper than we expect. Maybe it does not lie in tiny particles at all, but in the largest events in cosmic history. Events from the very first moments, during the most extraordinary instant that ever happened, the era of inflation. In a trillionth of a second, the universe expanded millions upon millions of times faster than the speed of light. A moment shorter than a blink, shorter than the time it takes you to think the word fast. And yet, in that instant, the universe transformed from something smaller than an atom into something larger than a ball. This was inflation, the most miraculous, most mind-bending event that has ever happened. Before we talk about inflation, we need to understand the problems it was invented to solve. The classical Big Bang theory comes with some deeply puzzling mysteries. For example, why is the universe so uniform? No matter which direction we look, the temperature of the cosmic background radiation is almost exactly the same. The differences are only a few parts in tens of thousands. That means regions separated by billions of light-years somehow once interacted, somehow shared heat and reached the same temperature. But how? According to the classical Big Bang, those regions were never in contact. Light simply did not have enough time to travel from one side to the other. They were outside each other's horizons. So how could they possibly have the same temperature? It is like having two pots of water on opposite sides of the world, never touching, yet both sitting at exactly 50 degrees Celsius. That is strange. It demands an explanation. The second problem is the flatness of the universe. Measurements show that the universe is almost perfectly flat. Not curved inward, not curved outward, but flat like a sheet of paper. In the classical Big Bang picture, for the universe to be this flat, the density of matter in the early universe had to be tuned with astonishing precision. A tiny deviation in the first second, and the universe would be wildly curved today. Why did it hit that exact value? It is like throwing a dart blindfolded and hitting a bullseye 100 meters away. Too lucky to be an accident. The third problem is the origin of structure. The universe is not completely uniform. Some regions are slightly denser, others slightly emptier. Those tiny differences eventually grew into galaxies. But where did they come from? Classical Big Bang theory has no answer. In 1980, physicist Alan Guth proposed a bold idea: inflation. He suggested that for an extremely brief moment, about 10 to the minus 36 seconds after the Big Bang, the universe went through a phase of insane expansion. Not ordinary expansion, but exponential expansion. In each tiny fraction of a second, the universe doubled in size. Then doubled again. And again. After 60 to 80 doublings, the universe had grown by millions upon millions upon millions of times. The strange part is that space itself expanded faster than light. That sounds like it violates Einstein's relativity, but it does not. Einstein said that no object can move through space faster than light. But space itself can expand as fast as it wants. There is no speed limit. It is like the surface of a balloon inflating, it can stretch faster than anything crawling on its surface could ever move. So where did the energy for this expansion come from? This is the magical part. It came from something called the inflation field. Not matter, not light, but a special form of energy filling space. Think of it like a tightly compressed spring, packed with potential energy. When the spring is released, that energy pours out. The inflation field has a remarkable property: its energy stays almost constant over time. Normally, when space expands, energy density should drop. Like blowing up a balloon, the air inside spreads out. But the inflation field does not behave that way. It replenishes itself. As space grows, the total energy actually increases. The bigger the space, the more energy there is. This provides an endless fuel source for expansion. During that fleeting moment, the universe expanded exponentially. A tiny region, originally smaller than an atom, became larger than a playground ball. Everything inside it was stretched. Tiny quantum fluctuations were stretched too, turning microscopic ripples into macroscopic ones. These ripples became the seeds of all future cosmic structure. After about 10 to the minus 32 seconds, the inflation field suddenly weakened, like a spring that has released all its energy. The remaining energy transformed into matter and radiation. The universe became hot, crowded with particles, flooded with light. This is the hot Big Bang we usually talk about. Inflation ended, and normal expansion began. Inflation solves all three problems at once. First, it explains why the universe is uniform. Before inflation, the universe was incredibly small, small enough for all regions to interact and equalize their temperature. Inflation then stretched those regions far apart. They look distant now, but they were once very close. Second, inflation explains why the universe is flat. Like inflating a small balloon into a huge one, the surface becomes flatter as it grows. Blow it up enough, and it looks almost perfectly flat. Inflation stretched the universe so dramatically that any initial curvature was flattened away. Third, inflation explains the origin of structure. Tiny quantum fluctuations in the inflation field were stretched into large variations. After inflation ended, these variations were imprinted onto the density of matter. Some regions were slightly denser, others slightly emptier. Gravity pulled matter toward the denser regions. Over time, they grew into galaxies, galaxy clusters, and the vast cosmic structures we see today. Inflation also explains something even more profound: how a universe can come from almost nothing. Before inflation, everything we can observe today fit into a region smaller than an atom, with almost no total energy. But the inflation field can generate energy as space expands. When inflation ended, that energy turned into matter. From nearly nothing, an entire universe emerged. There is a price, of course. The positive energy of matter is balanced by the negative energy of gravity. The total still adds up to zero. But now there is structure, complexity, and the possibility of stars, planets, and life. Evidence for inflation comes from many directions. The tiny fluctuations in the cosmic microwave background are exactly what inflation predicts. The flatness of the universe matches inflation's expectations. The large-scale distribution of galaxies follows the patterns inflation creates. More recently, scientists have even found hints of gravitational waves from inflation, though this remains debated. Inflation does not just explain our universe. It opens the door to countless others. Inflation may not stop everywhere at once. It could end in some regions while continuing forever in others. Each place where inflation ends becomes a universe of its own. We live in one of them. Far away, countless other universes may be forming, each with its own laws of physics, its own history. So now we understand how the universe was born. From quantum fluctuations, through a burst of wild inflation, to the hot Big Bang, to the formation of structure. From almost nothing, to 200 billion galaxies. A story that sounds miraculous, yet is grounded in mathematics, observation, and science. But now, let us talk about what we cannot see. Because 95% of the universe is invisible. So what is that unseen part? We have just traveled a long way, from a singularity to a vast universe. From nothing to 200 billion galaxies. A breathtaking story about the birth of everything. But that is only 5% of the story. What about the other 95%? It is completely invisible. It does not glow, it does not reflect light, it does not interact with anything we can see. So what does it mean that 95% of the universe is invisible? How can something make up most of the universe and yet be unseen? The answer depends on how we define the word nothing. Nothing sounds simple. You ask, what is in the box? Someone says, nothing. Easy enough. But in physics, it is far more complicated. There are at least 4 different kinds of nothing, each with its own meaning and its own importance. The first kind is everyday nothing. This is the absence of ordinary objects. You look at the space between Earth and the Moon, it looks pitch black, empty. No stars, no planets, no galaxies. But that space is not truly empty. It is filled with sunlight, with particles streaming from the solar wind, with magnetic fields, with radio waves, with leftover radiation from the Big Bang. Our eyes simply cannot see any of it. This is the simplest kind of nothing, the kind everyone intuitively understands. The second kind goes a bit deeper. It is empty space with no particles at all. Scientists call this a vacuum. You pump all the air out of a container, no oxygen molecules, no nitrogen, no carbon dioxide, nothing left. A perfect vacuum. And yet, even then, space is still not truly empty. Electromagnetic fields remain. Gravity is still there. Tiny ripples of space and time still exist. In this sense, a vacuum means no matter particles, but energy fields are still present. The third kind goes deeper still. This is the lowest possible energy state. Quantum physicists call it the ground state, or the quantum vacuum. All fields are at their minimum energy. No particles are excited, no waves are traveling. Everything seems calm and still. But even this is not absolute nothing. According to quantum mechanics, even the lowest energy state is full of fluctuations. Pairs of matter and antimatter pop into existence and vanish almost instantly. The quantum vacuum is not silent. It is restless, busy, and full of invisible activity. The fourth kind is philosophical nothing. No space, no time, no physical laws, nothing at all in the absolute sense. This is the state some people imagine before the Big Bang. Not emptiness, but the total absence of everything, even the possibility of existence. This kind of nothing lies beyond the reach of science. Science studies nature, things that can be measured and tested. Without space and time, there can be no experiments, no observations. This belongs to philosophy, not physics. So when scientists say the universe came from nothing, they are not talking about the fourth kind. They mean the third one. The lowest energy state, still filled with quantum fields, still filled with fluctuations, still filled with potential. From that state, through cosmic inflation, the universe was born. This distinction matters a lot. Many people hear, the universe came from nothing, and think science is making a ridiculous claim. How can nothing create something? But that reaction comes from a misunderstanding. Science is not talking about absolute absence. It is talking about a low energy state. That state is still something, just very different from anything we experience in daily life. Think of a perfectly calm lake. You look at it and see nothing happening. No waves, no ripples. But the water is still there. Toss a pebble in, and waves appear and spread outward. The waves did not come from absolute nothing. They came from water that was already present, just quiet. In the same way, the universe emerged from a quantum vacuum at low energy, not from total non-existence. Science can only deal with the first three definitions. First, no objects here, but objects could exist elsewhere. Second, no particles, but fields remain. Third, the lowest energy state, but still full of quantum fluctuations. All three can be studied, measured, and understood. The fourth kind lies outside science. There is no way to test a state with no space and no time. There is no experiment you can run on absolute nothing. So scientists leave that to philosophers and focus on what can actually be explored. And here is the truly fascinating part. Even within the three kinds of nothing that science can study, mysteries remain. The quantum vacuum, the lowest energy state, turns out to hide most of the mass and energy of the universe. In this nothing, in the empty spaces between stars and galaxies, lies 95% of everything. This is not magic or metaphysics. It is reality, observed, measured, and confirmed by countless experiments. How can something invisible have mass? How can nothing outweigh something? The answer lies in dark matter and dark energy, the two greatest mysteries in cosmology. They are not nothing. They are something we cannot see, cannot touch, and cannot interact with in familiar ways. They hide in the dark, yet they control the fate of the universe. Dark matter makes up about 25%. Dark energy makes up about 70%. Ordinary matter, everything we can see, including us, stars, and galaxies, is just 5%. Most of the universe is a dark ocean, filled with things we are only beginning to understand. This is not science fiction. It is the result of centuries of observation, measurement, and calculation. When astronomers track how galaxies move, they find invisible matter holding them together. When they measure how fast the universe is expanding, they discover something pushing it to expand faster and faster. These two discoveries completely overturned our understanding of the cosmos. So within this nothing lies 95% of the universe. Two invisible but incredibly powerful components. Two forces that shape structure and decide the ultimate destiny of everything. Dark matter keeps galaxies from flying apart. Dark energy drives the universe to expand forever. We do not know what they are, but we know they are there. We can measure their effects. We see their fingerprints everywhere. Now, let us explore where they come from, what they do, and why they matter so much. Everything you have ever seen in your life makes up just 5% of the universe, the blazing sun in the sky. 5%, the stars glittering at night. 5%, the earth beneath your feet. 5%, your body, your family, every person on this planet. All of it combined is still only 5%, the remaining 95% hides in the dark, completely invisible. This number is not a guess. It is the result of decades of observation, measurement, and careful calculation. Scientists have weighed the universe in many different ways, from many different angles, and they all arrived at the same shocking conclusion. Ordinary matter is only a tiny fraction. Most of the universe is made of two things we do not understand, cannot see, and cannot touch. The first component is dark matter, making up about 25% of the total, the second is dark energy, accounting for roughly 70%, together, these two invisible ingredients add up to 95%. We, along with everything we can see, are just the remaining 5%. It is like owning a huge house but only being able to see one small room. The rest is pitch black, mysterious, and unknown. The first question people usually ask is, how do we know these things exist if we cannot see them? The answer is gravity. Dark matter does not glow, does not interact with light, but it has mass. Mass creates gravity. Gravity pulls objects together. We can see the effects of that pull even if we cannot see the dark matter itself. The first evidence came from the way galaxies rotate. In the 1970s, astronomer Vera Rubin measured the rotation speeds of many spiral galaxies. She expected stars at the edges of galaxies to move more slowly than stars near the center. Just like in our solar system, planets farther from the sun orbit more slowly. Mercury, closest to the sun, moves the fastest. Neptune, the farthest, moves the slowest. But galaxies do not behave that way. Rubin discovered that stars at the edges of galaxies rotate just as fast as those near the center. Some even move faster. This completely contradicted expectations. At those speeds, galaxies should have flown apart. Centrifugal force should have flung the stars outward, like swinging a stone tied to a string. Spin it too fast and the string snaps, the stone flies away. So why do galaxies stay intact? There is only one reasonable explanation. There must be extra mass we cannot see. That hidden mass provides additional gravity, holding the galaxy together. Calculations showed that this invisible mass had to be about 5 times greater than all the visible matter combined. 5 times. This was the first time humanity realized that something enormous was hiding in the dark. The second line of evidence comes from gravitational lensing. Einstein predicted that massive objects bend space itself. Light traveling through this curved space gets deflected, much like light passing through a glass lens. Astronomers have observed this effect many times. When they look at a distant galaxy cluster, they see the light from even more distant galaxies bending around it, forming strange arcs and distorted shapes. From how strongly the light is bent, scientists can calculate the total mass of the foreground cluster. The result is always the same. The real mass is far greater than what we can see. All the stars, gas, and dust in the cluster are nowhere near enough to explain the bending. There must be additional invisible mass. This is independent evidence, not based on rotation speeds, yet it points to the same conclusion. Dark matter exists. The third piece of evidence comes from the large-scale structure of the universe. When we zoom out far enough, galaxies are not scattered randomly. They gather into clusters and superclusters, connected in an enormous cosmic web. Like a spider web, with dense nodes packed with galaxies, long filaments stretching between them, and vast empty voids in between. Scientists have simulated the formation of this structure on computers. They start with the early universe and let gravity pull matter together over time. But when they include only ordinary matter, the results do not match what we see. Structure forms too slowly. Even today, the universe should still be fairly smooth, without large galaxies. Only when dark matter is added do the simulations work. Dark matter begins clumping earlier than ordinary matter, creating a gravitational skeleton. Ordinary matter then falls into the gravitational wells carved out by dark matter, forming galaxies in those locations. With about 25% dark matter and 5% ordinary matter, the simulations produce a universe that looks exactly like what we observe. This is the strongest evidence we have so far. 3 independent lines of evidence, 3 different measurement methods, all pointing to the same numbers. 25% dark matter, 5% ordinary matter. This is not a coincidence. This is the reality of the universe we live in. Dark matter plays a crucial role in cosmic history. Without it, galaxies could not form. After the Big Bang, matter was distributed almost evenly. There were tiny fluctuations, but they were too small for ordinary matter to collapse under its own gravity. Radiation pressure pushed everything apart. But dark matter does not feel radiation pressure. It only responds to gravity. So it began clumping early, forming dense regions. These clumps of dark matter acted like gravitational pits. Ordinary matter fell into them, gathering as gas and dust. Gas collapsed into stars. Stars gathered into galaxies. The entire structure of the universe was built on a dark matter framework. Without that framework, there would be nothing. The universe would be a smooth cloud of gas, with no stars, no planets, and no life. So even though we cannot see it, dark matter is the reason we exist. It is the foundation of everything. Every galaxy is surrounded by a massive halo of dark matter, 10 times larger than the visible part. This halo holds the galaxy together, providing the extra mass needed to keep it from flying apart. But dark matter is only half the mystery. It accounts for 25%, which means 70% remains. That 70% is dark energy, something even stranger, harder to understand, and far more mysterious. Dark matter is still matter. It has mass. It creates gravity. It holds things together. Dark energy does the opposite. It pushes everything apart. It makes the expansion of the universe speed up over time. It acts like anti-gravity, a force that goes against everything we thought we knew. Dark energy is much, much crazier. There is a force tearing the universe apart. It pushes everything away from everything else at an ever-increasing speed. It is stronger than the gravity of hundreds of billions of galaxies. It makes up 70% of the total energy of the universe. It decides the ultimate fate of everything. We do not know what it is. We call it dark energy, but that is just a name for our ignorance. The story begins in 1998. 2 independent teams of astronomers were studying distant supernova explosions. They wanted to measure how fast the universe was expanding, and how much that expansion was slowing down. Because according to the theory at the time, gravity should slow the expansion. Like throwing a stone into the sky, gravity pulls it back, making it slow down and eventually fall. But the results were the exact opposite. The universe was not slowing down. It was expanding faster and faster. Distant galaxies were moving away from us at an accelerating rate. This was not a measurement error. Both teams, working independently, found the same result. The discovery shocked the scientific world. It went against every prediction, every expectation. There had to be some force pushing the universe to expand faster. That force had to be incredibly strong to overcome the gravity of the entire universe. Scientists called it dark energy, a temporary name for something they did not understand. The leaders of these studies later received the Nobel Prize in Physics in 2011 for this breakthrough discovery. So what is dark energy? This is one of the biggest questions in modern physics. There are several ideas, but none have been confirmed for sure. The simplest idea is that dark energy is the energy of space itself. Every cubic meter of space contains a tiny amount of energy. This amount does not change over time and does not depend on location. It is an inherent property of empty space, the way temperature is a property of matter. This idea is not new. Einstein proposed it more than 100 years ago and called it the cosmological constant. At the time, people believed the universe was static, neither expanding nor contracting. Einstein realized that his equations predicted the universe should collapse under gravity. To keep the universe static, he added an extra term to his equations, representing a repulsive force of space. Later, when Hubble discovered that the universe was expanding, Einstein called the cosmological constant the biggest mistake of his life. But it turns out Einstein was right all along, just for the wrong reason. The universe is not static, but the cosmological constant still exists. It does not hold the universe in place, it pushes it to expand faster and faster. The term Einstein added and then abandoned turned out to be the most important part of the equation. According to this idea, the more space there is, the more dark energy there is. As the universe expands, space increases, dark energy increases, which pushes the universe to expand even faster, creating more space, creating more dark energy. An endless feedback loop with no stopping point. This means the universe will expand forever, faster and faster. The second idea is that dark energy is not constant, but a dynamic energy field. Like the electromagnetic field or the gravitational field, this could be a new kind of field we have not discovered yet. It could change over time and vary from place to place. It might grow stronger, or it might weaken. In the future, it could behave very differently. Some scientists call this idea quintessence, a name borrowed from ancient philosophy. The idea is that an energy field fills the entire universe, similar to the inflation field in the early universe. This field is currently in a high-energy state, creating negative pressure that pushes space to expand. In the future, it could shift to another state and change the rate of expansion. The third idea is even stranger. Dark energy might not be something new at all, but a sign that Einstein's theory of gravity breaks down on the largest scales. Gravity might behave differently across billions of light years. We may need a deeper, more fundamental theory to explain how galaxies move. But this idea has serious problems. Einstein's theory has been tested countless times and has always passed with extraordinary precision. The recent detection of gravitational waves also matches Einstein's predictions perfectly. It is extremely hard to change the theory without losing all of its successes. The biggest problem with dark energy is that we cannot measure it directly. Unlike dark matter, dark energy does not pull things together with gravity. It creates a pushing pressure. This pressure only becomes noticeable on truly enormous scales, hundreds of millions of light-years across. On smaller scales, gravity is still stronger and keeps everything bound together. Because of that, we cannot study dark energy in a laboratory. We cannot create it, control it, or examine it directly. All we can do is observe its effects on the universe as a whole. We measure the expansion rate, the distribution of galaxies, the cosmic microwave background. From these clues, we infer that something must be making up 70% of the energy of the universe. The impact of dark energy is profound. It determines the future of the universe. About 5 billion years ago, the universe was still slowing down. Gravity was in control. But around 5 billion years ago, dark energy began to dominate. Since then, the expansion of the universe has been accelerating. In the future, distant galaxies will slip beyond our observable horizon. Their light will never reach us again. The universe will become darker and more isolated. Eventually, only our local group of galaxies will remain visible. Everything else will fade into darkness. Far further ahead, trillions of years from now, even the stars in our own galaxy will burn out. The universe will grow cold, dark, and empty. Dark energy will be the only thing left, pushing the last remaining particles farther and farther apart forever. This is the cold death, the most likely ending for our universe. But everything depends on the true nature of dark energy. This remains one of the greatest unanswered questions in science. Understanding it could trigger a revolution in physics, like quantum theory, like relativity. It might even lead us to a unified theory, a theory that explains everything. For now, all we know is that it exists, it makes up 70%, and it pushes the universe to expand. Everything else is mystery. A vast mystery that fills most of the universe and decides the fate of all things. So far, we have talked about matter, energy, and the ingredients of the cosmos. Now it is time to talk about structure. How does the universe take those ingredients and turn them into shape, order, and the beauty we see today? We have learned about matter, about energy, about the ingredients that make up the universe. Now, let us step back and look at the whole picture. From very far away, so far that we can see billions of galaxies at once, the universe does not look like random chaos. It has a shape. It has structure. It looks like a gigantic cosmic web, long filaments stretching between dense knots of galaxies, with vast empty regions in between. This is the grandest architecture that has ever existed, built not by intention, but by gravity, by time, by the fundamental laws of physics. In 1995, astronomers carried out a bold experiment. They pointed the Hubble Space Telescope at a patch of sky that appeared completely empty. No bright stars. No prominent galaxies. Just a dark, seemingly blank piece of space. They kept the telescope fixed on that spot for many days, collecting every faint photon of light they could. The result was shocking. In that supposedly empty region, they discovered more than 3,000 galaxies. Each tiny dot of light in the image was not a star, but an entire galaxy containing hundreds of billions of stars. These galaxies were so distant that their light had traveled for billions of years to reach Earth. We were looking deep into the past, back to a time when the universe was young. This image is called the Hubble Deep Field. Later, astronomers repeated the experiment, pointing Hubble at other regions of the sky. Every time, they found thousands of galaxies. There were no truly empty patches. In every direction, at every angle, the universe was filled with galaxies. From these images, scientists estimated how many galaxies exist in the observable universe. They measured the area of sky, counted the galaxies, and scaled that number up to the entire sky. The final result was about 100 to 200 billion galaxies, a number so vast that the human mind struggles to grasp it. Each galaxy contains between 100 billion and 400 billion stars. If we take an average of 200 billion stars per galaxy, and multiply that by 200 billion galaxies, we get a total of 40,000 billion stars in the observable universe. That is more than the number of grains of sand on all the beaches on Earth. More than the number of drops of water in all the oceans. So many that you could never count them, even if you lived 1,000 lifetimes. Our own galaxy, the Milky Way, is just one of these. An ordinary galaxy, nothing particularly special. It contains about 200 to 400 billion stars. The Sun is just one of them, a modest star out in the suburbs. Earth orbits the Sun. We live on Earth. Which means we are a tiny speck, on a tiny rock, orbiting a tiny star, in a fairly average galaxy, among hundreds of billions of galaxies. That realization can make us feel incredibly small. But at the same time, it fills us with awe at the vastness of the universe. Each galaxy may host billions of planets. Each planet could potentially support life. The possibility that there are other civilizations out there is remarkably high. We may not be alone. What is truly remarkable is that galaxies are distributed quite evenly throughout the universe. Look to the north, and you see roughly 100 billion galaxies. Look to the south, and you see roughly the same. East, west, it makes no difference. No direction is special. No region is dramatically denser or emptier than another. The universe looks the same no matter where you look. Scientists call this the cosmological principle. It states that on sufficiently large scales, the universe is uniform, independent of location and independent of direction. Everywhere is essentially the same. There is no center, no edge, no preferred direction. This is a crucial observation, because it tells us that the universe has no privileged structure. However, on smaller scales, the universe is not uniform at all. Galaxies are not scattered randomly. They gather into groups. A galaxy cluster can contain dozens, hundreds, or even thousands of galaxies bound together. Our Milky Way belongs to a small group called the local group, which contains about 50 galaxies. Clusters themselves gather into superclusters. The Laniakea supercluster, our cosmic home, contains around 100,000 galaxies. It spans roughly 500 million light-years. All the galaxies within it are moving toward a common gravitational center, pulled by an enormous concentration of mass. These superclusters are connected to one another by long filaments, forming what we call the cosmic web. From a distance, the universe resembles soap foam, with huge empty bubbles surrounded by thin walls of galaxies. Or a spider web, with long threads connecting dense nodes. Or a sponge, with vast holes woven through solid structures. These empty regions are truly empty. They can span hundreds of millions of light-years with no galaxies at all. Just thin gas, dark matter, and empty space. These are the loneliest places in the universe. No light. No life. Almost nothing. So how did this cosmic web form? It began with tiny fluctuations in matter density shortly after the Big Bang. Dark matter clumped together first, forming a gravitational skeleton. Ordinary matter fell into these gravitational wells, giving rise to galaxies. Over time, gravity pulled galaxies closer together, forming clusters, superclusters, and filaments. Regions that started out with slightly lower density became the vast cosmic voids. This process took billions of years. The early universe was nearly uniform. Slowly, structure emerged. The first galaxies formed about 200 million years after the Big Bang. They were small, chaotic, and filled with hot gas. Over time, they collided and merged, growing larger and more organized. Today, we see massive, stable, and beautiful galaxies. And this structure is still evolving. Galaxies continue to move, collide, and merge. Our own Milky Way is on a collision course with the Andromeda Galaxy. In about 4 billion years, they will crash into each other and form a larger galaxy. This is a normal process in the universe. So there are hundreds of billions of galaxies, each containing hundreds of billions of stars. Numbers too large to truly comprehend. And yet, they are not arranged randomly. They form structures, patterns, and breathtaking beauty. From the chaos of the early universe, gravity created order. And with such staggering numbers, all looking the same in every direction, a natural question arises. Where is the center? The answer might knock you off balance: everywhere is the center. That sounds absurd, right? How could everywhere possibly be the center? And yet, that is exactly how the universe works. This is one of the strangest and most counterintuitive ideas in cosmology. When people hear that the universe is expanding, most imagine a normal explosion. Like a firework going off, blasting fragments outward in every direction from a single central point. The debris flies through space, farther and farther from the center. In that picture, the explosion point is clearly the center. But the Big Bang was not like that. The universe did not expand from a single point in space. It was not something that exploded and spread into empty space around it. Instead, space itself is expanding. There is no central point. There is no special location where the Big Bang happened. The Big Bang happened everywhere, all at once. This sounds abstract, but there is an analogy that helps. Think about the surface of a balloon. Draw dots on the surface, each dot representing a galaxy. Now blow the balloon up. What happens to the dots? They move away from one another. Every dot sees all the other dots receding. But no dot is special. No dot is the center of the expansion. Each dot sees itself as stationary, while all the others move away. From the perspective of each dot, it is at the center. The key detail is that the dots are not moving across the surface of the balloon. They are not sliding over the rubber. Instead, the rubber itself is stretching, pulling the dots apart. The space between them increases, even though each dot stays where it is on the surface. The universe works the same way. Galaxies are not flying through space. They are mostly at rest, or moving slowly due to gravity. But the space between them is expanding. The farther apart two galaxies are, the faster the space between them expands. That is why more distant galaxies recede faster, not because they are moving faster, but because there is more expanding space in between. Back to the balloon. There is something fascinating here. From the point of view of any dot, all other dots move away at speeds proportional to their distance. The farther a dot is, the faster it recedes. This is exactly what we observe in the real universe, described by Hubble's law. Of course, this analogy is only two-dimensional. The surface of a balloon has just two directions, east-west and north-south. The real universe has three dimensions of space, east-west, north-south, up-down. So instead of the balloon's surface, we must imagine the entire balloon expanding. Every point inside moves away from every other point. Every point is a center from its own perspective. In reality, we must add a fourth dimension, time. The universe is a four-dimensional expanding spacetime. But the human brain cannot truly picture four dimensions, so we rely on two- or three-dimensional analogies to make sense of it. The core idea is this: there is no special place in the universe. Here on Earth, we see galaxies receding in all directions. An alien in the Andromeda galaxy sees galaxies receding in all directions too, including our Milky Way. A being in a distant galaxy 10 billion light-years away sees the same thing. Everyone sees themselves at the center. This does not mean we truly are at the center. It means the concept of a center does not apply to the universe. It is like asking, where is the center of Earth's surface? The question itself makes no sense. Earth's surface has no center and no edge. You can travel around it forever without ever reaching a special point. Another way to picture this is to imagine the universe as an infinite elastic fabric. Place chess pieces on it, each one representing a galaxy. Now stretch the fabric in all directions. Every piece moves away from every other piece. But none of them is the center. There is no point on the fabric where the stretching began. In fact, the universe may be infinite in space. If that is the case, it was always infinite, even before expansion. The Big Bang did not turn a finite universe into an infinite one, it simply made it expand. An infinite thing that expands is still infinite, only the distances between points grow larger. Even if the universe is finite, it still has no center. Just like the surface of a balloon is finite but has no center on the surface. You can travel around it without ever encountering an edge or a special point. A three-dimensional universe can be finite yet unbounded, much like the two-dimensional surface of a balloon. This also means there is no edge of the universe in the usual sense. No wall, no curtain, no stopping point. You cannot fly to the edge of the universe and look beyond it, because there is no beyond. The universe is everything. Space exists only inside the universe, not outside it. There is, however, something called the cosmic horizon. This is the limit of what we can see, not the limit of the universe itself. Light from galaxies beyond that horizon has not had enough time to reach us yet. But that does not mean the universe ends there. It only means we cannot see farther. Every observer has their own horizon. Our horizon is different from the horizon of an alien in another galaxy. They can see galaxies we cannot, and we can see galaxies they cannot. No horizon is special. Every location has its own, all equally valid. So in summary, the universe does not expand from a single point. Space itself expands everywhere. Every observer sees themselves at the center. There is no true center, and no true edge. Everywhere is equal, everywhere is the same in a cosmological sense. This can make us feel small. We are not special in terms of location. Not at the center, not at the edge, just one ordinary point among countless others. But at the same time, it makes us special. Because if everywhere is the center, then we are at the center too. From our perspective, the universe expands around us. We are the observers, the awareness, the point from which the universe is perceived. So with this strange kind of expansion, no center, no edge, what shape does the universe actually have? The shape of the universe is nothing like anything you can hold in your hands. It is not a square, not a circle, not a box. It is not even a sphere. The shape of the universe is about how space itself bends, how straight lines behave, how geometry works on the largest scales imaginable. This is one of the deepest questions in all of science. There are three main possibilities for the shape of the universe, and each one leads to a completely different future. The first possibility is a closed universe, also called positively curved. The easiest way to understand it is to imagine the surface of a ball. That surface curves in one direction, a positive curvature. If you draw a triangle on the surface of a sphere, the sum of its three angles is greater than 180 degrees. This is very different from the flat geometry we learn in school, where the angles of a triangle always add up to exactly 180 degrees. In a closed universe, if you travel straight in one direction long enough, you eventually return to where you started, like walking all the way around the Earth. A closed universe is finite in size, but it has no boundary. There are no walls, no edges. You can keep going forever without hitting an end, yet the total amount of space is still finite. The second possibility is an open universe, or negatively curved. The best mental image is a saddle shape. It curves upward in one direction and downward in the perpendicular direction. That is negative curvature. Draw a triangle on a saddle-shaped surface, and the sum of its angles is less than 180 degrees. In an open universe, if you travel straight in one direction, you never come back. The universe keeps expanding forever and is infinite in size. Not just very large, but truly endless. There is no final point, no edge to reach. You can travel forever and still not arrive at a boundary. The third possibility is a flat universe. This is the special case balanced between the other two. Space does not curve at all, and geometry works exactly like the textbook version. Draw a triangle and the angles add up to 180 degrees. Parallel lines never meet and never drift apart. A flat universe is also infinite in size. You can travel straight forever, never returning, never hitting an edge. It is like an open universe, but with simpler geometry. So which one is our universe? The answer is written into the cosmic microwave background, the faint afterglow of the Big Bang. Scientists have measured the temperature of this radiation across the entire sky with incredible precision. From tiny fluctuations in that temperature, they can calculate the curvature of space itself. The result is astonishing. The universe appears to be almost perfectly flat. The measurements show flatness with an uncertainty of only about 0.4%. That means any curvature, if it exists at all, is extremely small. For all practical purposes, we cannot distinguish it from being perfectly flat. This has profound implications. For the universe to be flat, the density of matter and energy must be exactly equal to a specific value known as the critical density. Just a little more, and the universe would be positively curved and closed. Just a little less, and it would be negatively curved and open. But at exactly the critical value, the universe is flat. The chance of the universe randomly having exactly the critical density is incredibly small. It is like balancing a rock on the tip of a needle. Move it the tiniest bit, and it falls. So why is the universe so perfectly flat? Inflation provides the answer. During the inflationary period, the universe expanded at an unimaginably fast rate. Like blowing up a tiny balloon into a massive one, the surface becomes flatter as it grows. No matter what the original curvature was, inflation stretches space until it looks almost perfectly flat. That is why we observe a flat universe today. Still, there are hints of mystery. Some anomalies in the data suggest the universe might be very slightly positively curved. In the year 2019, a team of scientists analyzing data from the Planck satellite found that the cosmic background radiation appeared a bit stronger than expected. One possible explanation is a closed universe, gently curved like a sphere. But this result is controversial. Other teams analyzing the same data do not find clear evidence for curvature. It could be statistical noise or measurement uncertainty. Or it could be a hint of new physics. For now, there is no definitive conclusion. If the universe is truly flat, what does that mean? It means the universe is infinite in space. No edge, no final boundary. You could travel forever in one direction and never hit a wall. There is always more space, more galaxies, more stars. It also means the universe will expand forever. It will never stop and never collapse back in on itself. Galaxies will drift farther and farther apart. Over time, the universe will grow colder, darker, and emptier. This is the big freeze, the cold death of the cosmos. What if the universe is closed and finite? In that case, the universe could eventually stop expanding and begin to contract. Gravity would finally win, pulling everything back together. The universe would collapse into a single point, like the Big Bang running in reverse. This is the big crunch. But with dark energy pushing the universe to expand faster and faster, the big crunch now seems unlikely. Even if the universe is closed, dark energy appears strong enough to overpower gravity. Expansion would continue regardless of curvature. If the universe is open and negatively curved, the outcome is similar. Expansion goes on forever, accelerating under the influence of dark energy. Nothing can stop it. The universe still ends in a big freeze. So no matter the shape, the universe seems headed toward the same fate, endless expansion, growing colder, darker, and emptier. Dark energy, not geometry, appears to decide the final outcome. Still, the shape of the universe matters deeply in theory. It tells us about the universe's global structure. It tests our ideas about inflation. It helps explain why the universe looks the way it does today. Future measurements will be even more precise. We may discover that the universe is not perfectly flat after all. There could be a tiny amount of curvature, too small to detect right now. Or the universe may turn out to be flawlessly flat, exactly as inflation predicts. Either way, the fact that we can measure the shape of the universe at all is extraordinary. Just a few hundred years ago, humans believed Earth was the center of everything. Today, we measure the curvature of all space and time. We know the universe spans 93 billion light-years, contains about 200 billion galaxies, and is almost perfectly flat. That is a triumph of science. Knowing the shape of the universe also lets us do something else, determine its age. The expansion rate, the curvature of space, and the contents of the universe are all connected. By running the cosmic clock backward, we can calculate how long ago the universe began. How do you figure out the age of something that enormous? You cannot count rings in a trunk the way you do with a tree. You cannot dig up fossils and date them. The universe does not come with a birth certificate. So how did scientists arrive at the number 13.8 billion years, with an accuracy down to tens of millions of years? They rely on two independent methods, both grounded in direct observation, not guesswork. What is remarkable is that these two methods arrive at almost exactly the same answer. That agreement is powerful evidence that the number is right. The first method measures how fast the universe is expanding. When Edwin Hubble discovered that galaxies are moving away from us, he also uncovered a simple rule: the farther a galaxy is, the faster it is receding. Speed is proportional to distance. Double the distance, double the speed. Triple the distance, triple the speed. This relationship is called the Hubble constant. It tells us how quickly the universe is expanding. Once you know that number, you can rewind cosmic history. If galaxies are moving apart today, then in the past they must have been closer together. Go far enough back, and eventually everything converges to a single point. The time it takes to go from that point to today is the age of the universe. The basic idea is simple: distance divided by speed gives time. Do this for many galaxies at many different distances, average the results, and you get an estimate of the universe's age. But there is a catch. The universe has not been expanding at a constant rate. Early on it expanded faster, then slowed down under the pull of gravity, and more recently it has begun speeding up again because of dark energy. That makes the calculation a bit more complicated. You have to account for how the expansion rate changes over time. There is another challenge as well: measuring the distances to galaxies is hard. You cannot use a ruler. You cannot fly there and count. Astronomers use a technique called the cosmic distance ladder. They start by measuring distances to nearby stars using parallax. Those stars are then used to calibrate variable stars, stars that brighten and dim in a regular cycle. The period of that cycle is linked to the star's true brightness. If you know how bright a star really is and how bright it appears, you can calculate its distance. It is like looking at a light bulb from far away: the farther it is, the dimmer it looks. If you know how powerful the bulb is, its apparent dimness tells you how far away it must be. Astronomers repeat this process for thousands of stars and hundreds of galaxies, building a vast map of cosmic distances. Next, they measure how fast those galaxies are moving away by studying their light. Light from a receding galaxy is stretched, shifting toward the red end of the spectrum. The amount of this redshift reveals the galaxy's speed. With both distance and speed in hand, they can calculate the Hubble constant and from it the age of the universe. Using this method, the current estimate comes out to about 13.7 to 13.8 billion years. But there is some debate. Different measurements give slightly different values for the Hubble constant. This could be due to measurement errors, or it could hint at physics we do not yet fully understand. It is one of the hottest topics in modern astronomy. The second method is completely different. It analyzes the cosmic microwave background, faint radiation left over from about 379,000 years after the Big Bang. By measuring its temperature and tiny fluctuations, scientists can extract a wealth of information about the early universe. This radiation is like a baby picture of the cosmos. From it, scientists can tell how hot the universe was, how dense it was, how uniform it was. They can see the small density ripples that would later grow into galaxies. Using theories of the Big Bang, cosmic inflation, and particle physics, they run detailed computer simulations. They start at the Big Bang and let the universe evolve according to the laws of physics, then see what it should look like after 379,000 years. They compare the simulation to the real cosmic microwave background and adjust the parameters until the two match. One of the most important parameters is the age of the universe. Change the age, and the entire simulation changes. A younger universe looks different from an older one. Only one value produces a perfect match with what we observe. The European Space Agency's Planck satellite made the most precise measurement ever. Its result: the universe is 13.799 billion years old, with an uncertainty of only about 40 million years. That is astonishing precision. 40 million years sounds like a lot, but compared to 13.8 billion, it is just about 0.3%. It is like knowing the age of a 50-year-old person to within a few months. Two independent methods, one looking at motion in the present, the other looking at ancient light, both converge on the same number, about 13.8 billion years. That is not a coincidence. It is strong evidence that the universe truly had a definite beginning. In the past, many people believed the universe was eternal, existing forever with no starting point. Observations tell a different story. The universe has a birthday. Exactly 13.8 billion years ago, everything began with the Big Bang. This number also fits with other measurements. The oldest stars we have found are about 13 to 13.5 billion years old. They cannot be older than the universe itself, so the universe must be slightly older. 13.8 billion years fits perfectly. The oldest globular clusters, ancient groups of stars, show similar ages. The most distant galaxies we can observe appear to have formed about 13.5 billion years ago. All of these pieces line up, like parts of a single, enormous puzzle. All of this means the universe is not eternal. It had a beginning. Before 13.8 billion years ago, there were no stars, no galaxies, no atoms. There was only extremely high energy, extreme temperature, and space compressed to an unimaginably small size. From that state, everything else emerged. Over 13.8 billion years, the universe has transformed almost beyond recognition. From a point smaller than an atom, it expanded to a span of 93 billion light-years. From pure energy, it created matter. From chaos, it built structure. From simplicity, it produced complexity. From lifelessness, it gave rise to consciousness. We happen to live at a special moment in cosmic history. Stars are still shining. Galaxies are still beautiful. The universe is still relatively young, only about 1/3 of the way to the time when the last stars will burn out. We are lucky to exist during the universe's golden age. But 13.8 billion years is not the limit of what we can see. Even though the universe is 13.8 billion years old, the observable universe is much larger than that. How is that possible? Light has been traveling for 13.8 billion years. Yet the observable universe is 93 billion light-years across. How can that be? It sounds like it breaks math, right? Light moves at a constant speed, the universe is 13.8 billion years old, so we should only be able to see 13.8 billion light-years away. But in reality, we can see more than twice that distance. This is one of the strangest consequences of an expanding universe. Let's start with a distant galaxy. Call it Galaxy A. When the universe was only 1 billion years old, Galaxy A emitted a beam of light toward us. That light traveled at the speed of light, the fastest speed in the universe. Nothing can go faster. It kept moving, without stopping, for 12.8 billion years, until it finally reached our telescopes today. So does that mean Galaxy A is 12.8 billion light-years away? Not quite. Today, Galaxy A is about 30 billion light-years from us. How is that possible? Because while the light was traveling toward us, the space between us and Galaxy A was expanding. Imagine an ant crawling along a rubber band while the band is being stretched. The ant moves forward, but the rubber band stretches behind it. The ant still makes progress toward its goal, but it takes longer because the path keeps getting longer. By the time the ant arrives, the distance is much greater than when it started. Light works the same way. It moves toward us, but space itself is expanding. Every cubic meter of space between us and Galaxy A is growing. So the light has to cross a much longer distance than the original separation. By the time the light finally reaches us, Galaxy A has drifted far, far away. Detailed calculations show that a galaxy whose light took 13.8 billion years to reach us is now about 46.5 billion light-years away. This distance is called the radius of the observable universe. The full diameter is twice that, roughly 93 billion light-years. The observable universe is everything we can see, in principle. Light from galaxies within this region has had enough time to reach us. What about light from galaxies beyond that? It has not arrived yet. Maybe it will in the future, maybe it never will. This boundary is called the cosmic horizon. It is like the horizon at sea, where you cannot see any farther because the Earth curves away. The cosmic horizon is where you cannot see farther because light has not had enough time to arrive. It is not the edge of the universe, just the edge of what we can observe. What is fascinating is that this horizon changes over time. Every second that passes gives light from farther regions one more second to travel. So the cosmic horizon slowly expands. Galaxies that were once beyond our reach drift into view. We see a little more of the universe each day. But there is a catch. The universe is not just expanding, it is expanding faster and faster because of dark energy. This creates a strange situation. Very distant galaxies are moving away from us faster than the speed of light. Not because they are flying through space faster than light, but because the space between us and them is expanding faster than light can overcome. Light from those galaxies is still trying to reach us, but space is stretching even faster than it can travel. It is like swimming against a strong current. You keep swimming forward, but the current is stronger than you are, so you are carried backward. Light does the same thing. It keeps moving toward us, but in reality it is being pushed farther away. These galaxies lie beyond another boundary called the cosmic event horizon. Light from there will never reach us, no matter how long we wait. This boundary is about 16 billion light-years away. Anything beyond it is permanently invisible to us. Worse still, this boundary is shrinking. As the expansion of the universe accelerates, more and more galaxies cross it. They slowly fade, shift toward the red, and then disappear from view forever. We are gradually losing galaxies. Astronomers today can see galaxies tens of billions of light-years away. In a few billion years, some of them will become too faint to observe. In a few tens of billions of years, most will vanish. In a few 100 billion years, nearly the entire observable universe will be empty. In the end, only our local group of galaxies will remain. The Milky Way, the Andromeda Galaxy, and a few dozen smaller companions. They are close enough for gravity to hold them together, safe from the pull of cosmic expansion. Over time, they will merge into a single massive galaxy. An astronomer living in that far future, inside this merged galaxy, will look up at the sky and see what? Only their own galaxy, alone in an endless darkness. No other galaxies anywhere. The cosmic microwave background will have stretched so much that it can no longer be detected. Every piece of evidence for the Big Bang will be gone. They will conclude that the universe contains only one galaxy, their own. They will know nothing of a larger cosmos. Nothing of cosmic expansion. There will be no way to discover the truth. All of cosmology will be impossible. We are lucky to live now. At a time when the universe is old enough to form complex structures, yet young enough to still preserve evidence of its past. A time when galaxies are close enough to be observed. When the background radiation is still strong enough to detect. A few 100 billion years from now, all of this will be gone. This also means there may be things that disappeared before we ever existed. In the early universe, there may have been strange phenomena, fascinating structures, now far beyond our observable horizon. We will never know they existed. The full history of the universe may remain a mystery forever. So the observable universe is 93 billion light-years across, yet the number of galaxies we can see is shrinking. We live in a special window of time, when the universe reveals its secrets. Before now, it was too simple. Afterward, the evidence will fade away. Only now can we learn. And still, the observable horizon is not the edge of the universe. Beyond it, the universe continues. Perhaps infinitely. Perhaps filled with countless galaxies we will never see. And farther still, there may be countless other universes beyond our own. Beyond the edge of our observable horizon, beyond everything we can see, there may exist countless other universes. Each one as vast as our own, filled with hundreds of billions of galaxies and trillions upon trillions of stars. Yet each might operate under completely different rules. This is the idea of the multiverse, one of the boldest and most controversial concepts in modern physics. This idea is not wild fantasy. It arises naturally from inflation, which we talked about earlier. Remember, inflation was a brief moment of insane expansion during the universe's very first second. An inflation field, packed with energy, drove space to expand faster than light itself. Then, suddenly, that field weakened, its energy turned into matter, and the hot Big Bang began. But why should inflation have ended everywhere at the same time? It could have stopped in one region, creating our universe, while continuing in others. Those regions kept expanding wildly, racing away from us at unimaginable speeds. Then, at some point, inflation stopped there too, giving birth to another universe. That universe had its own Big Bang, its own history, its own galaxies. According to the theory of eternal inflation, this process never fully ends. Somewhere, inflation is always happening. Somewhere, new universes are always being born. Like a pot of boiling water, bubbles constantly form and rise. Each bubble is a universe. We live inside one bubble. All around us are countless others, each isolated, each with its own reality. And it gets stranger. Each universe may have different laws of physics. In our universe, the electron has a specific mass, light travels at a specific speed, gravity has a specific strength. These numbers are called physical constants. They determine how the universe works. But in some theories, these constants are not fixed. They are set by how the inflation field decays. In each universe, the field decays differently, producing different constants. In one universe, electrons are heavier. In another, light is slower. In yet another, gravity is stronger. The result is that every universe has its own story. In this one, the constants allow stars to form, galaxies to grow, and life to emerge. In another, the nuclear force is too strong and no stable atoms can exist. In another, gravity is too weak and nothing ever clumps together. Most universes would be sterile, empty, uninteresting. We live in a rare universe where the constants are just right for complexity. Physicist Max Tegmark has classified the multiverse into 4 levels. Level 1 is the simplest, regions beyond our observable horizon that follow the same laws of physics. We cannot see them because light has not had enough time to reach us, but they exist and obey the same rules. Level 2 includes universes born from inflation with different laws of physics. These are the bubble universes we just described. Each has its own constants and its own history. They are completely isolated, unable to interact with or observe one another. Level 3 comes from quantum mechanics. According to the many worlds interpretation, every time a quantum event occurs, the universe splits into branches. Each branch corresponds to a different possible outcome. When you flip a coin, the universe splits into 2, one where the coin lands heads, and one where it lands tails. Both are real. Both exist in parallel. Level 4 is the most abstract. Every possible mathematical structure exists as its own universe. Every consistent set of physical laws is realized somewhere. This is the idea that mathematics does not just describe reality, it is reality. All of these ideas are bold and astonishing. They stretch our concept of reality to almost unimaginable scales. But they share a serious problem: they cannot be tested, at least not with today's technology. How do you test the existence of another universe that you can never see, never interact with, never send a signal to? By definition, other universes lie beyond the observable horizon. No information from them can ever reach us. No experiment can directly detect them. Some scientists argue that this is not science. Science requires testable hypotheses, observable predictions, and the possibility of being proven wrong. The multiverse fails these criteria. It feels more like philosophy than science, more metaphysics than physics. Others argue that the multiverse is an unavoidable consequence of theories that are already well supported. Inflation explains many observations. Quantum mechanics has been confirmed millions of times. If you accept these theories, you must accept their consequences, including the multiverse. What is more, the multiverse offers an explanation for something deeply puzzling: why the physical constants are so perfectly tuned for life. Why is the electron not slightly heavier or lighter? Why is gravity not a bit stronger or weaker? Change any constant by a small amount and life becomes impossible. In a single universe, this seems absurdly lucky, like winning the most impossible lottery imaginable. But in a multiverse with countless universes, each with different constants, some are bound to have the right combination. We live in one of them, not because of a miracle, but because of selection. Only universes with the right constants can have observers. The debate continues. Some scientists believe that in the future we may find ways to test the multiverse, perhaps through subtle imprints in the cosmic background radiation, perhaps through deeper mathematical insights. Others believe the multiverse will forever remain untestable, beyond the reach of science. Right now, we do not know. Our universe might be unique, alone in the void. Or it might be just one bubble among countless others in an endless sea of eternal inflation. Maybe every time you make a decision, the universe splits into two branches. Maybe every mathematical structure exists as a physical reality. We do not know. But simply asking these questions, simply contemplating these possibilities, shows how far we have come. From ancient people who thought the earth was flat, to today, when we debate the existence of countless parallel universes. It is an extraordinary journey of knowledge. So we have talked about the structure of the universe. About 200 billion galaxies, about its flat shape, about its age of 13.8 billion years, about the observable horizon, about the possibility of the multiverse. It is all vast. It is all overwhelming. But within all that immensity, there is one small and profound question: in this vast universe, are we alone? We have talked about the vastness of the universe. About 200 billion galaxies stretching across space. About countless trillions of stars burning brightly. About endless planets circling those stars. With numbers that staggering, a natural question arises. Is Earth really the only place with life? In a universe 93 billion light-years wide, containing hundreds of billions of galaxies, is there really just this one tiny planet with bacteria, plants, animals, humans? It sounds hard to believe. Like saying that in the entire ocean, only a single drop of water contains salt. It just does not make sense. Before we look for life elsewhere, we need to understand what life needs in order to exist. Not miracles, not gods, but specific conditions, chemical ingredients, and physical laws. Life does not appear randomly. It needs the right recipe. The first condition is liquid water. Not ice, not vapor, but water in its liquid form. Why? Because water is an incredible solvent. Molecules dissolve in it, move freely, collide, and react. Life on Earth began in water. The first cells formed in the oceans. Every living thing contains water, from 60% to 90% of its total mass. Liquid water exists only within a narrow temperature range, from 0 to 100 degrees Celsius at normal pressure. Too cold and it freezes. Too hot and it boils into vapor. So a planet must orbit its star at just the right distance. Not so close that it becomes a furnace, not so far that it turns into a freezer. This region is called the habitable zone. Earth sits right inside the Sun's habitable zone. Mars is a bit farther out, colder, but still close to the edge. Venus is a bit closer in, far too hot. We happen to be in just the right place. The second condition is the right chemical elements. Life is built on carbon, a remarkable element capable of forming an enormous variety of complex molecules. Carbon combined with hydrogen creates hydrocarbons. Combined with oxygen it forms carbohydrates. Combined with nitrogen it creates amino acids, the building blocks of proteins. Add phosphorus for DNA, add sulfur for certain specialized proteins. These 6 elements, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are the foundation of life. They make up more than 95% of the mass of every living organism. Without them, there is no life as we know it. But where did these elements come from? Hydrogen formed shortly after the Big Bang. It is the simplest element, just 1 proton and 1 electron. Helium formed early as well. But heavier elements like carbon, oxygen, and nitrogen were not there at the beginning. They were forged in the hearts of stars. The first generation of stars formed from hydrogen and helium. They burned intensely, squeezing hydrogen nuclei together to form helium. Then they fused helium into carbon. The process continued, creating oxygen, nitrogen, silicon, iron. When a star dies, it explodes as a supernova, blasting these elements into space. The resulting cloud of gas mixes with the original hydrogen and helium, forming a second generation of stars. These stars contain carbon, oxygen, and nitrogen. When planets form around them, those planets inherit the same elements. The Sun is a third-generation star, maybe even a fourth. About 2% of its mass consists of heavy elements. Earth formed from the disk of material around the young Sun and inherited those elements. That is why we have carbon to build our bodies, oxygen to breathe, nitrogen for proteins, phosphorus for DNA. The third condition is an energy source. Life needs energy to maintain order, to push back against entropy. On Earth, the primary energy source is the sun. Plants use photosynthesis to turn light into sugar. Animals eat plants, or eat other animals that ate plants. The entire food chain is powered by sunlight. But sunlight is not the only option. Deep on the ocean floor, where sunlight never reaches, there are hydrothermal vents. Hot water rich in chemicals pours out from within the planet. Bacteria live there, using chemical energy instead of light. This is proof that life can exist without sunlight. The fourth condition is long-term stability. Life needs time to develop. Going from simple molecules to complex cells takes millions of years. Going from single-celled organisms to multicellular life takes billions of years. A planet must remain stable long enough for this process to unfold. Earth is fortunate. We have a large moon that stabilizes our planet's rotation. We have a massive Jupiter that helps shield us from asteroid impacts. We have a strong magnetic field that blocks harmful cosmic radiation. Together, these factors create a stable environment where life can thrive. On Earth, life appeared very early. The planet formed about 4.5 billion years ago. During its first billion years, Earth was battered by asteroids, molten, and lacking a stable atmosphere. But by about 3.8 billion years ago, we already see evidence of life. The first bacteria, simple cells, but undeniably alive. This means life emerged almost as soon as conditions allowed it. Only a few 100 million years passed between Earth cooling down and life beginning. That suggests life is not rare. It does not require miracles. Given the right conditions, life appears on its own. So in a vast universe, how many planets have the right conditions? Astronomers have already discovered thousands of planets beyond our solar system. Many of them lie within habitable zones. Many are similar in size to Earth. Some may have liquid water. Conservative estimates suggest there could be billions of Earth-like planets in the Milky Way alone. Multiply that by 200 billion galaxies, and we end up with countless trillions of potentially life-friendly worlds. The number is almost impossible to comprehend. Could life have appeared earlier elsewhere? Absolutely. Heavy elements existed when the universe was only a few billion years old. Second-generation stars already contained carbon, oxygen, and nitrogen. Planets orbiting them could have hosted life 10 billion years ago, 6 billion years before Earth. Where would such civilizations be now? Humanity has had advanced technology for only a few thousand years. A civilization that started a billion years earlier would be so advanced that we can barely imagine it. They might have solved every scientific problem. They might travel between stars. They might have become effectively immortal. They might have vanished into higher dimensions. So life could appear early. It could appear in billions of places. The necessary conditions are not rare. The ingredients are everywhere. The recipe has been proven to work at least once. Logic suggests that life should be common. And yet, where is everyone? Why have we not met anyone yet? One afternoon in 1950, the physicist Enrico Fermi was having lunch with his colleagues. They were talking about aliens, about the possibility of other intelligent life in the universe. Suddenly, Fermi asked a simple but profound question: so where is everybody? That question became famous and is now known as the Fermi paradox. It captures a deep contradiction. The universe is vast, filled with countless opportunities for life, so why do we see no evidence at all? In 1961, the astronomer Frank Drake tried to put numbers to this mystery. He wrote down an equation to estimate how many intelligent civilizations in the Milky Way might be capable of communicating. The equation multiplies several factors together: how many stars form each year, how many of those stars have planets, how many planets per system lie in the habitable zone, the fraction of those planets that develop life, the fraction of life that becomes intelligent, the fraction of intelligent civilizations that develop communication technology, and the average lifetime of such civilizations. The problem is that we only know the first few factors with any confidence. How many stars are in the Milky Way? Roughly 200 to 400 billion. How many stars have planets? Almost all of them, thanks to the Kepler telescope, which discovered thousands of exoplanets. How many planets lie in the habitable zone? Estimates suggest billions in our galaxy alone. But after that, things get murky. What fraction of planets actually develop life? We have no idea. It could be 100%, it could be 1%, it could be 0.0001%. We have only one example: Earth. What fraction of life becomes intelligent? Again, we do not know. On Earth, life has existed for about 3.8 billion years, yet intelligent beings have appeared only in the last few million. That step might be incredibly hard. Then there is the lifetime of a civilization, the most important factor and the biggest unknown. Humanity has had radio technology for about 100 years. How much longer will we last? 1,000 years? 1 million years? Or just a few more centuries before we wipe ourselves out? Depending on the values you choose, the Drake equation can give answers ranging from just us to millions of civilizations. There is no definitive result. Still, logic suggests that with billions of potentially life-friendly planets, the chance that we are completely alone is very small. So where are they? Why have we not detected any signals? Why has no spaceship landed on Earth? Why is the sky so silent? There are many possible explanations. The first explanation is distance. The nearest star system is about 4 light-years away. That sounds close, but it is an enormous distance. With our current technology, it would take tens of thousands of years to get there. The radio waves we have been broadcasting have traveled only about 100 light-years. Within that bubble are just a few thousand stars, a tiny fraction compared to the 200 billion in the Milky Way. There could be thousands of civilizations out there, but separated by thousands or millions of light-years. They may never detect one another. Like people living on distant islands across a vast ocean, each believing they are alone. The second explanation is that life is rarer than we think. The step from chemistry to biology might be extraordinarily difficult. Earth may have been unusually lucky, with a large moon, Jupiter acting as a shield, a strong magnetic field, and a safe position in the galaxy away from intense radiation. It might take trillions upon trillions of planets to produce one that truly works. In that case, we might be unique, at least in this part of the Milky Way. The third explanation is self-destruction. The transition from primitive technology to advanced technology may be a dangerous phase. Nuclear weapons, climate change, uncontrolled artificial intelligence. Perhaps most civilizations survive only a few hundred years after developing technology, then destroy themselves. In that case, the universe could be filled with the ruins of dead civilizations, and very few living ones. The fourth explanation is that they do not want to make contact. Advanced civilizations may know something we do not. Broadcasting signals into space might be dangerous, drawing the attention of hostile forces. They may choose to remain silent and hidden. Or they may follow a rule of non-interference, allowing young civilizations to develop on their own without outside influence. The fifth explanation is that they have already been here, but we did not recognize them. A civilization millions of years ahead of us might no longer use radio waves. They could communicate with neutrinos, with gravitational waves, or with something we have not invented yet. We might be listening on the wrong frequencies, looking in the wrong direction, searching for the wrong thing. Or perhaps they arrived in forms we never expected. Not metallic spaceships, but bacteria carried on meteorites. Not little green beings, but disembodied artificial intelligence. Not radio signals, but traces hidden in our own DNA. Despite the lack of evidence, scientists continue to search. The SETI program, the Search for Extraterrestrial Intelligence, has been listening to the sky for decades. It scans millions of frequencies, analyzes billions of signals, searching for patterns that do not look natural. So far, nothing definitive. In 1977, there was the famous "wow" signal, a powerful burst lasting 72 seconds, but it never repeated. It could have been interference, it could have been a natural phenomenon, it could have been something else entirely. We do not know. More recently, mysterious fast radio bursts have been detected from distant galaxies. They are incredibly powerful, extremely brief, and sometimes repeat in patterns. Many hoped they were signs of intelligence. But most scientists believe they come from magnet-Rs, a type of neutron star with an extraordinarily strong magnetic field. Some people argue that instead of just listening, we should send messages. The METI program, Messaging Extraterrestrial Intelligence, deliberately broadcasts signals toward nearby stars. These messages encode information about humanity, about Earth, about mathematics and science, in the hope that someone receives them, understands them, and responds. This idea is controversial. Stephen Hawking warned that attracting attention could be dangerous. We do not know who is out there. They could be friendly, they could be hostile. Earth's history shows that when two civilizations meet, the less advanced one often suffers. Is it worth the risk? Others argue that it is already too late. We have been leaking radio and television signals into space for about 100 years. Anyone capable of finding us already has. Sending deliberate messages does not change much. And the chance of encountering a hostile civilization may be very small. Any civilization that survives long enough to travel between stars likely has learned to control violence and war. So are we alone? Right now, no one knows for sure. Maybe we are. Maybe we are not. Logic, probability, and the Drake equation all suggest that life should be common. But the silence of the sky suggests that something may be missing from our understanding. Perhaps we are the first. Perhaps we are the last survivors. Perhaps we are being watched in silence. Perhaps the answer is right next to us, and we are simply not looking in the right place. The question remains open. The search continues. And there is an even deeper question beneath it all, one that goes beyond whether there is life out there at all. There is a question even deeper than the search for life beyond Earth. It is not about who might be out there, but about why we are here at all. Why does the universe allow life to exist? Why do the laws of physics fit together so perfectly that they can produce stars, planets, and human beings? Was the universe made for us? Scientists call this the anthropic principle. It sounds lofty, but the core idea is simple. The universe must have properties that allow observers to exist. Because we are here observing the universe must be capable of producing us. Otherwise, we would not be here to ask the question. There are two versions of this principle. The weak version says that the universe must allow observers. This is a fairly straightforward statement. We observe the universe, so the universe must have conditions that permit life, at least in some places and at some times. There is nothing surprising about finding ourselves in such a universe. The strong version goes further. It says that the universe must produce observers. Not just allow them, but actively give rise to them. The universe has a purpose, a direction, aimed toward the emergence of consciousness. This claim is far more controversial and sounds more philosophical or religious than scientific. Why do people even consider ideas like this? Because when we look closely at the laws of physics, we find something strange. The physical constants appear to be tuned with extraordinary precision. Change them by even a tiny amount, even 1%, and the universe would be completely different, incapable of supporting life. Take a few examples. The strong nuclear force holds protons and neutrons together inside atomic nuclei. It is stronger than the electromagnetic force that pushes protons apart. The strength of the strong nuclear force is a constant. Increase it by 2%, and deuterium, an isotope of hydrogen with 1 proton and 1 neutron, becomes too stable. All the hydrogen in the early universe would turn into deuterium. There would be no hydrogen left to form water or to fuel stars. No life. Decrease it by 5%, and deuterium cannot form at all. Without deuterium, stars cannot synthesize helium, carbon, or oxygen. No heavy elements, no rocky planets, no life. Another example is the fine structure constant. This number describes the strength of the electromagnetic force. Its value is about 1 divided by 137. Why this strange number? No one knows. But change it by just 4%, and carbon cannot form inside stars. No carbon means no carbon-based life. There are many more examples. The mass ratio of the proton to the electron. The strength of dark energy. The initial density of matter in the early universe. All of them lie within an extremely narrow range. Outside that range, the universe either collapses almost immediately, or expands too fast for anything to clump together, or produces only hydrogen and helium with no heavy elements. Physicists calculate that the chance of randomly getting all these constants exactly right is extraordinarily small. It is like throwing a dart blindfolded and hitting the bullseye from 1 kilometer away. Then doing it 20 times in a row, every throw hitting the center. The probability is so low that pure chance feels unsatisfying. So how do we explain it? There are 3 main possibilities. The first is that we are incredibly lucky. The universe just happened to have the right constants, for no reason at all. Pure chance. We exist to be amazed by it because only a lucky universe like this one could produce observers. Other universes with the wrong constants have no one in them to be surprised. But this explanation makes many people uneasy. It is like saying, I won the lottery 20 times in a row, it was just luck. It is possible, but skepticism feels reasonable. The second possibility is the multiverse. There are countless universes, each with different constants. Most of them are sterile, empty, and uninteresting. But with an enormous number of universes, a few are bound to have the right combination. We live in one of those, not because it is special, but because of anthropic selection. Only universes with the right constants can have observers. It is like planets. There are countless planets, most of them lifeless. But with so many, at least a few will have the right conditions. We live on one of those. Earth was not specially designed for us, we can only exist on a planet with suitable conditions. In the same way, with countless universes, we can only exist in one with the right constants. The universe was not designed for us, we are simply the result of selection. Only this kind of universe allows us to exist. This explanation is appealing because it removes the sense of coincidence. There is no miraculous luck, just pure statistics. With enough universes, every possibility happens somewhere. The problem is that we cannot observe these other universes. They lie beyond our reach. So this remains a hypothesis, not a proven fact. The third possibility is intentional design. Some entity, some higher intelligence, adjusted the constants to create life. The universe is not random, it was designed. Its purpose is to produce consciousness, to produce us. Many religious believers favor this explanation because it fits with the idea of a creator. But from a scientific perspective, it is not a strong explanation. It makes no testable predictions and cannot be verified. It simply pushes the question back a step. Who designed the designer? Why did they design the universe this way? Where did they come from? Moreover, if the universe was designed for life, why is it so wasteful? About 95% of the universe is dark matter and dark energy, useless for life. Most of the universe is cold, empty space. Only a tiny fraction consists of stars and planets, and most of those cannot support life. This does not look like an efficient design. For these reasons, most scientists lean toward the multiverse explanation. It accounts for fine-tuning without invoking a deity. It fits naturally with inflationary theory. It makes logical sense. But it has not been proven. The deeper issue is whether science can answer this question at all. It may be that physical constants are not truly free, but constrained by a deeper theory. One day we might discover a unified theory that explains why the electron has this mass, why light has that speed. In that case, the mysterious fine-tuning disappears. Everything becomes a necessary consequence of mathematics. Or maybe not. Maybe the constants really are free, randomly set in each universe. In that case, we must accept that our universe is just one among many, selected by the anthropic principle. Right now, we do not know. We know that the universe allows life. We know that it requires precise tuning. But why it is this way remains a mystery. What is certain is that we are not the physical center of the universe. Earth is not the center. The Sun is not the center. The Milky Way is not the center. We are just an ordinary point in a vast expanse of space. But in terms of meaning, in terms of consciousness, we may be special. We are the universe becoming aware of itself. We are how the universe understands itself. So far, we have talked about the past, the origin of the universe. About the present, its structure and life within it. Now we come to the final part, the boundary. Where is the edge of the universe? What lies beyond it? And is it possible to go outside at all? Everything has a boundary, right? A room has walls. A city has borders. A nation has boundary lines. Earth has a surface. Even the solar system has a region where the sun's influence fades away. Everything we know has a beginning and an end. So the universe must have a boundary too, it must have an edge. The question is, where is that edge? What lies beyond it? And is it possible to leave the universe? You step into the fastest spaceship ever built. You fly straight in one direction. No stopping, no turning back, just forward forever. After 1 billion years, 10 billion years, 100 billion years, what do you encounter? A wall? A curtain? A sign that says, end of the road? Or do you just keep flying through empty space forever? The answer depends on the shape of the universe. But before we get there, we need to clearly separate two ideas that are often confused: the observable horizon and the edge of the universe. The observable horizon is the limit of what we can see. Light from more distant galaxies has not had enough time to reach us yet. That horizon is about 46.5 billion light-years away. But this is not the edge of the universe. It is only the edge of our view. Like standing on a beach, you can see the horizon a few kilometers away, but the ocean does not end there. It continues far beyond. So where is the true edge of the universe? The answer surprises many people. There may be no edge at all. The universe may be infinite in space. We know that the universe is very close to flat. In flat geometry, space can extend infinitely in all directions. There is no final point. You fly straight ahead and you never reach an edge. Not because you loop back to where you started, but because there is always more space in front of you. This is hard to grasp. Our brains are used to finite things. Everything we see has boundaries. But mathematics allows infinite space. There is no logical contradiction. It is just difficult to imagine. An open universe, with negative curvature, is also infinite. In a sense, it is even more expansive than a flat universe. Space curves outward and stretches on forever. No stopping point, no edge, no border. But what about a closed universe, one with positive curvature? In that case, space is finite. The total volume is a specific number. And yet, here is the strange part: there is still no edge. Think about the surface of Earth. It has a finite area, about 510 million square kilometers. But you can travel around it forever without ever finding an edge. No point on the surface is special. There are no borders. You just keep going and eventually return to where you started. A closed universe works the same way, but in 3 dimensions instead of 2. Fly straight in one direction long enough and you return to your starting point. Not because you turned around, but because space itself curves into a closed loop. Like Pac-Man leaving the screen on the right and reappearing on the left, but in 3 dimensions. Of course, the distances involved are unimaginably large. A closed universe, if it exists, would be far bigger than the observable universe. It would take hundreds of billions of light-years to go all the way around, longer than the age of the universe so far. So we cannot test this directly. So here is the summary. A flat or open universe is infinite and has no edge. A closed universe is finite, but still has no edge. In all 3 cases, there is no wall, no curtain, no stopping point. The idea of an edge of the universe does not exist in the usual sense. This also means you cannot leave the universe. Because there is no outside. The universe is everything. Space exists inside the universe, not beyond it. Asking what is outside the universe is like asking what is north of the North Pole. The question itself has no meaning. There is, however, one small caveat. So far, we have been talking about the observable universe, or even the entire universe that emerged from our Big Bang. But according to multiverse theories, our universe may be just one bubble in an ocean of eternal inflation. In that case, there are other universes outside ours. But that outside means something very different. Those universes are not located in our space. They have their own space and their own time. You cannot fly from one universe to another in a regular spaceship, because they do not exist within the same space. Imagine 2 sheets of paper lying parallel to each other. Each sheet has its own 2-dimensional surface. An ant on one sheet cannot crawl to the other by moving along the surface, because the sheets are not connected in 2 dimensions. The ant would have to jump through a 3rd dimension, one it does not even know exists. In a similar way, different universes may exist side by side in a higher dimensional space. We cannot reach them by traveling through our 3 dimensions of space. We would need to move through a 4th or 5th dimension, one we do not have access to. So in practical terms, our universe has no reachable edge. No wall to crash into. No sign that says, "Do not go further." You can fly forever, or eventually loop back around, depending on the shape. But you never escape. Some people find this claustrophobic, trapped inside the universe with no way out. Others find it liberating. No walls. No ultimate boundary. Always more space to explore, or at least the illusion of it. One last question. Can the universe expand? Does new space appear? Was there less space before and more space now? The answer is no, not in that sense. If the universe is infinite, it has always been infinite, even when it was young. Infinity multiplied by any number is still infinity. If the universe is finite, its total volume increases over time as it expands, but no new space is added from the outside. There is no outside to add from. Expansion means the distances between points increase. The space between galaxies grows. Not because new space appears, but because existing space stretches. Like pulling on a rubber sheet. The area increases, but no new rubber is created. The same rubber just stretches. So there is no edge of the universe. No wall, no boundary, no final point. Only space that goes on forever, or curves back into itself. And yet the question still lingers. If there were a boundary, what would be on the other side? Even without an edge, the question still lingers, what is outside the universe? It feels so natural that almost everyone asks it at some point. But maybe this is the wrong question from the very beginning. Maybe it has no answer, not because we do not know enough yet, but because the question itself does not mean anything. When you ask, what is outside the universe, you are assuming that there is an outside. You are assuming there is some kind of space beyond the universe, a place the universe sits in. Like a box inside a room inside a house inside a city. So what, exactly, is the universe inside of? Here is the problem. Space is not something that contains the universe. Space is part of the universe. It belongs to the universe, it does not exist independently beyond it. Like the surface of a sphere, it does not lie inside another surface. For an ant living on that surface, the surface itself is everything that exists. So asking, what is outside the universe, is a lot like asking, what is north of the North Pole? The North Pole is the northernmost point. There is nothing farther north. Not because a wall blocks the way, but because the concept of north stops making sense at that point. In the same way, outside may lose its meaning when we talk about the universe as a whole. Still, we can try to think about possible answers, even if they stretch or challenge our logic. The first possibility is nothing. Not empty, like a vacuum, but non-existence in the absolute sense. No space, no time, no matter, no energy, nothing at all. Not even the concepts of is, or is not. This is a kind of nothingness the human brain cannot truly imagine. Every time we try to picture nothing, we end up imagining an empty space. But space itself is already something. This kind of nothing does not even include space. Some philosophers call this absolute nothingness. It is not the same as a quantum vacuum, not the same as empty space, not the same as anything physics can study. Physics studies what exists. Absolute nothingness is the complete absence of existence. The second possibility is other universes. In multiverse theories, our universe may be just one bubble in a vast sea of eternal inflation. Around us, outside, in some abstract sense, there could be countless other universe bubbles. Each with its own Big Bang, its own laws of physics, its own history. But outside here does not mean somewhere in our three-dimensional space. These universes are not billions of light years away in any direction. They are completely separate. Like two parallel pages in a book, each page has its own surface, but they are not connected through that surface. To go from one universe to another, you could not travel using the familiar 3 dimensions. You would have to move through another dimension, a higher one. That leads to the third possibility. The third possibility is higher dimensions. Our 3-dimensional universe might exist within a 4-dimensional, 5-dimensional, or even higher dimensional space. Like a 2-dimensional sheet of paper existing within the 3-dimensional space around it. We experience only 3 dimensions of space, east to west, north to south, up and down. Add time as another dimension, and we get 4-dimensional spacetime. But there may be additional spatial dimensions we do not perceive. These dimensions are not large like the ones we know. They may be curled up extremely small, smaller than an atom. String theory suggests that the universe actually has 10 or 11 dimensions. 3 large spatial dimensions we can see, plus 6 or 7 tiny curled up ones. We do not notice the small dimensions because they are so compact. Like a thin wire viewed from far away, it looks like a one-dimensional line, but up close, you see it has a tiny circular thickness. In this picture, what is outside our 3-dimensional universe could be a higher dimensional space called the bulk, or the volume space. Our universe would be a 3-dimensional membrane, often called a brane, floating inside a higher dimensional bulk. That leads to the fourth possibility, the bulk of string theory itself. In some versions of string theory, our universe is a 3-dimensional brane drifting through a higher dimensional bulk. There may be many other branes floating in that same bulk. Each brane would be its own universe. These branes could be close together or far apart in the higher dimensions, even though they are not connected through ordinary 3-dimensional space. Sometimes, 2 branes might collide. Such a collision would release enormous energy, potentially triggering a Big Bang. This is one alternative idea for the origin of our universe, different from cosmic inflation. In this model, what is outside our universe is the bulk itself, containing higher dimensions and possibly other branes, other universes. We cannot see the bulk because light, matter, everything we know is trapped on our 3-dimensional brane. Only gravity may be able to leak into the bulk. This could explain why gravity is so weak compared to the other forces. Electromagnetism and the nuclear forces are confined to the brane, their energy concentrated. Gravity spreads out into the bulk, becoming diluted. If this is true, it could be an indirect clue that higher dimensions really exist. All of these ideas are speculative. We have no direct evidence for higher dimensions, for the bulk, or for other branes. They arise from mathematical theories, not from confirmed observations. But they give us ways to think about outside the universe, without completely breaking logic. The deeper issue remains the same. Our brains evolved to survive in 3 dimensions of space. We are used to everything being inside something else, everything having an outside. So naturally, we ask what the universe is inside of. But maybe that question simply does not apply at cosmic scales. Maybe the universe is not inside anything at all. It just exists, on its own, needing no container. Its space is all the space there is. Its time is all the time there is. There is no outside, because outside is a concept that only makes sense within space, and space exists only within the universe. Or maybe there really is a bulk, higher dimensions, a multiverse. We do not know yet. For now, outside the universe remains a mystery. It may be a meaningless question, or it may point toward the deepest discoveries about reality itself. And if higher dimensions are part of the answer, then we have to go further. How many dimensions does the universe really have? Why do we only see 3? And is there any way to prove that these extra dimensions exist at all? We live in a 3-dimensional world. You can move east or west, north or south, up or down. 3 independent directions. 3 dimensions of space. On top of that comes time, the 4th dimension. You move forward through time, from the past into the future. Altogether, we live in 4-dimensional spacetime. But that might not be the whole story. The universe may have more dimensions than we can see. There could be 5, 6, 7 dimensions, or even more. They are hidden from view, not because they are far away, but because they are incredibly small. This idea comes from string theory, one of the most ambitious theories in physics. It tries to unify every force, every particle, everything in nature into a single mathematical framework. In string theory, the fundamental particles are not points, but tiny vibrating strings. Each way a string vibrates creates a different particle. Vibrated one way, you get an electron. Vibrated another way, you get a photon. All the diversity of matter comes from strings vibrating in different patterns, much like guitar strings vibrating at different frequencies produce different sounds. But for the mathematics of string theory to work, more than 3 dimensions of space are required. Specifically, the theory needs 10 or 11 dimensions, depending on the version. 3 familiar dimensions of space, 1 dimension of time, plus 6 or 7 extra spatial dimensions. Without these extra dimensions, the equations break down and the theory collapses. So where are these extra dimensions? Why do we not see them? The answer is that they are curled up extremely small, smaller than an atom, smaller than a proton. So small that at the scale we live in, they are impossible to detect. The easiest way to picture this is to imagine a garden hose. From far away, it looks like a one-dimensional line. But up close, you see that it has thickness. An ant walking on the hose can move forward or backward, but it can also move around the circumference. That second direction is real, but it is small and curled into a loop. In the same way, every point in our 3-dimensional space could have extra tiny dimensions curled up within it. You cannot travel far in these dimensions, only move around them over extremely small distances. The shapes of these curled-up dimensions are called calibi, Yau manifolds, complex geometries full of twists, folds, and holes. The specific shape of a calibi, Yau manifold determines how strings vibrate, and therefore which fundamental particles exist. Change the shape, and you get a universe with different particles, possibly with different laws of physics. There are thousands, maybe millions of possible calibi, Yau shapes, each corresponding to a possible universe. All of this is mathematically beautiful. But is there any evidence? How do we know these extra dimensions are real and not just a mathematical game? For now, we cannot observe them directly. The dimensions are too small to probe with any instrument we have. Even the most powerful particle accelerator ever built, the Large Hadron Collider, does not reach energies high enough to explore these scales. We would need energies millions of times greater. Still, there could be indirect evidence. One major clue is gravity, which is strangely weak. Compared to the other forces, gravity is incredibly feeble. The electromagnetic force between 2 electrons is stronger than their gravitational attraction by a factor of 10 to the 42. That is an enormous number, and it begs for an explanation. One idea is that gravity is weak because it leaks into extra dimensions. The other forces, electromagnetism and the nuclear forces, are confined to our 3 dimensions of space. They cannot access the curled-up dimensions. Gravity is different. It can spread into all dimensions. Think of water leaking from a pipe into the surrounding soil. Inside the pipe, the water is concentrated and the pressure is high. Once it leaks out, it spreads and becomes weaker. Gravity does the same thing. It spreads into higher dimensions, so we only feel a small fraction of it in 3-dimensional space. This leads to an interesting consequence. At very small distances, close to the size of the curled-up dimensions, gravity could be much stronger than we expect, possibly as strong as the other forces. The Large Hadron Collider has been searching for signs of this. One possible sign would be the creation of tiny black holes. In 3 dimensions, it takes enormous energy to form a black hole. But with extra dimensions, gravity becomes stronger at small scales, and black holes could form at much lower energies. The collider could, in principle, create microscopic black holes in particle collisions. That sounds dangerous, but these black holes would be incredibly small and extremely short-lived. They would evaporate almost instantly through Hawking radiation, in about 10 to the minus 27 seconds. Not nearly enough time to swallow anything. They would leave behind only subtle traces in the detectors. So far, no such black holes have been seen. That puts limits on the models. If extra dimensions exist, they must be smaller than a certain threshold. Or maybe they do not exist at all. Or maybe we simply need higher energies to detect them. Another possible sign is the existence of Kaluza-Klein particles. These are heavier versions of ordinary particles that also vibrate in the curled-up dimensions. Like sound, which has a fundamental tone and higher harmonics. Ordinary particles are the fundamental tone, Kaluza-Klein particles are the harmonics. If they exist, these particles would be much more massive. Too heavy to be produced in ordinary collisions. But the Large Hadron Collider might have enough energy. Physicists are combing through the data, looking for hints of unfamiliar particles. So far, there is nothing. No tiny black holes, no Kaluza-Klein particles, no clear evidence for extra dimensions. This does not mean they do not exist. It only means that if they do, they are different from the simplest predictions. They may be smaller, shaped differently, or require even higher energies to reveal themselves. String theory remains a theory, not an experimentally confirmed description of reality. It is mathematically elegant, it unifies many ideas, and it explains some deep puzzles. But none of its predictions have yet been verified by observation. That is why many scientists remain skeptical. They want evidence, not just beautiful equations. Others believe string theory is pointing in the right direction, and that we simply have not tested it in the right way yet. Maybe we need larger accelerators. Maybe we need more precise cosmological observations. Maybe the clues are hidden in gravitational waves, in the cosmic background radiation, or in subtle ripples of spacetime itself. The debate continues. But the idea of higher dimensions goes beyond string theory alone. It appears in many areas of physics. It offers an explanation for why gravity is so weak. It opens the door to the possibility of parallel universes. It allows us to think about what lies outside our universe in a meaningful way. Higher dimensions could lead to other universes. Parallel brains floating in a higher dimensional bulk. Each brain a separate universe, with its own laws and its own history. They may be close together in higher dimensions, yet completely unreachable through ordinary three-dimensional space. Could it ever be possible to travel between them? Somewhere, in a parallel universe, there is another version of you reading these words. Maybe they made a different choice at some crucial moment in their life. Maybe their universe runs on slightly different laws of physics. Maybe they are wondering whether there is a way to reach our universe, just as you are wondering whether you could reach theirs. This question is not just science fiction. Physicists have seriously explored the possibility. They search for cracks in the fabric of spacetime, shortcuts that connect distant regions, possibly even different universes. These cracks are called wormholes, also known as Einstein-Rosen bridges. The idea comes straight from Einstein's equations. In 1935, Einstein and Nathan Rosen discovered that the mathematics of relativity allows tunnels through spacetime. Imagine space as a sheet of paper. 2 points on the paper are very far apart. But fold the paper, punch a hole through it, and suddenly those 2 points are close together. A wormhole works in much the same way. It connects 2 points in space through a tunnel that is far shorter than the normal route. Instead of traveling for billions of light years, you could pass through a wormhole and appear instantly at your destination. Like taking a tunnel through a mountain instead of climbing up and down. Even more astonishing, wormholes might connect not just 2 regions of the same universe, but 2 completely different universes. One end here, the other end somewhere else entirely. Step through, and you arrive in a new world with its own history, possibly even its own laws of physics. Wormholes could even link black holes to white holes. A black hole is a region of space with gravity so intense that everything falls in and nothing escapes, not even light. A white hole is the opposite concept, a theoretical object that spews everything out and allows nothing in. No one has ever observed a white hole, but the mathematics allows them to exist. According to theory, a black hole might not end in an infinitely dense singularity, as we usually imagine. Instead, it could be the entrance to a wormhole, leading to a white hole on the other side. Matter falls into the black hole, travels through the tunnel, and emerges from a white hole in another universe. That is the Einstein-Rosen bridge. It sounds incredible, but there is a major problem. Wormholes are extremely unstable. Calculations show that they would collapse almost instantly, faster than light could pass through them. Not even a single photon would make it across before the wormhole snapped shut. To keep a wormhole open, you need something very strange, negative energy matter. Not just negative mass, but negative energy. This kind of matter would push instead of pull, creating anti-gravity. It would counteract the collapse of the wormhole and hold the tunnel open. The problem is that we do not know whether negative energy matter truly exists. Quantum mechanics allows tiny, temporary amounts of negative energy through vacuum fluctuations, but not nearly enough, and not for long enough, to stabilize a wormhole. What would be required is a large, stable supply of negative energy, and we have no idea how to produce it. On top of that, no one has ever observed a white hole. Every astronomical observation points to black holes only. If white holes existed, they should release enormous amounts of energy and be easy to detect. Yet there is no sign of them. Maybe they do not exist. Maybe they are extremely rare. Maybe they only appeared in the early universe and then vanished. Recently, a new idea has emerged linking wormholes to quantum entanglement. Two particles can be entangled, meaning their states are connected no matter how far apart they are. Measure one particle, and you instantly know the state of the other, even if they are billions of light years apart. Einstein hated this idea and famously called it spooky action at a distance. But experiments have proven it is real. Quantum entanglement exists. Some physicists have proposed that two entangled particles are actually connected by an incredibly tiny, incredibly short-lived wormhole. If that is true, then wormholes are not rare at all. They are everywhere, at the quantum scale, connecting entangled particles. But they are far too small to travel through. Somehow, they would need to be enlarged, turning a quantum wormhole into a macroscopic one. No one knows how to do that. So wormholes, at least with our current technology, are not practical. Are there other ways to travel between universes? One possibility involves higher dimensions. We have talked about extra dimensions curled up beyond our perception. If there were a way to access them, it might be possible to move through higher dimensional space and reach another universe brain. Like an ant on a sheet of paper that normally crawls in 2 dimensions, but if it learns to jump, it could leap to another sheet entirely. Of course, we do not know how to jump into higher dimensions. We are not even sure they exist. But if they do, and if we could access them, they might allow travel between parallel universes. Another idea is faster than light travel. According to relativity, nothing can move through space faster than light. But there is a loophole. Space itself can move at any speed. The Alcubierre drive is a theoretical concept that exploits this idea. The concept is to compress space in front of a spacecraft and expand space behind it. The ship sits inside a bubble of flat spacetime, carried along by a wave of space itself. From the outside, the ship appears to move faster than light. From the inside, it is not moving at all, so relativity is not violated. The catch, once again, is negative energy. And a lot of it. More energy than the mass of an entire galaxy. No one knows how to obtain such energy. So the Alcubierre drive remains firmly in the realm of science fiction. In the end, it may take a civilization far more advanced than ours. One that has existed for millions or billions of years, that has solved every major scientific problem and mastered every energy source. Such a civilization might know how to create negative energy matter. It might know how to open wormholes. It might know how to move through higher dimensions. We, with technology only a few hundred years old, are like Stone Age humans trying to build a spaceship out of rocks. We have the mathematics and the theories, but not the tools. Maybe in a few thousand years, or a few million years, humanity, or whatever comes after us, will figure it out. Or maybe it will never happen. Maybe some fundamental laws of physics forbid travel between universes. Maybe universes are completely isolated, forever unreachable from one another. Maybe we are permanently confined to the universe that gave birth to us. For now, the answer is simply that we do not know. Wormholes are theoretically possible but extraordinarily difficult. Higher dimensions might exist but remain unproven. Faster than light travel requires unimaginable energy. All of it is beyond our reach. And yet, the remarkable thing is that we can even ask these questions. We can write equations, calculate possibilities, design experiments to test them. Even if we cannot travel there yet, we know how to ask the right questions. And that is the first step. So far, we have talked about the beginning, about the Big Bang, about inflation, about the origin of matter. About structure, about galaxies, about the shape of the universe, about life. About boundaries, about the cosmic horizon, about higher dimensions, about the multiverse. Now we come to the final and deepest question of all. How does it end? How will the universe die? Everything has an ending. Stars burn through their fuel and fade into darkness. Planets cool down and become barren. Galaxies collide, merge, and eventually drift apart. Even black holes, the most seemingly eternal objects in the universe, slowly evaporate. Nothing lasts forever. Everything has a beginning, and everything has an end. The universe is no exception. We have talked about birth, about the Big Bang, about those miraculous first moments. Now it is time to talk about death. About the final day of the universe. About the moment when everything comes to an end, or transforms into something entirely different. This is not a sad story, it is an inevitable truth. Every story has an ending. The universe will too. Scientists have calculated, simulated, and predicted the universe's ultimate fate. They look at the rate of expansion, the amount of matter, dark energy, everything we know about the cosmos. Then they fast-forward the cosmic movie, watching what unfolds over billions, trillions, even quadrillions of years. The answer depends on factors we do not fully understand yet. But there are three main scenarios, three ways the universe could end. Will the universe end in ice, in fire, or be torn apart? This is not a philosophical question. It is a scientific one, with concrete predictions based on observations, calculations, and the laws of physics. Each scenario leads to a completely different future. Each depends on the true nature of dark energy, something we still do not fully understand. The first scenario is called the Big Rip, the universe torn apart. In this case, dark energy is not a constant. It grows stronger over time. At first, it simply pushes galaxies away from each other. But gradually, it becomes more powerful, accelerating faster and faster. Eventually, it becomes strong enough to overcome every binding force. Gravity can no longer hold galaxies together. Nuclear forces can no longer hold atoms together. Everything is ripped apart. The second scenario is called the Big Crunch, the universe collapses. In this case, dark energy weakens or disappears. Gravity takes over. The universe stops expanding and begins to contract. Galaxies rush toward each other. Space itself shrinks. Temperatures skyrocket. In the end, everything collapses into a single point, like the Big Bang played in reverse. The third scenario is called the Big Freeze, the universe freezes. It is also known as heat death. In this case, dark energy remains constant, just as it appears to be now. The universe continues expanding forever. Galaxies drift farther and farther apart. Stars burn out. Black holes evaporate. Eventually, all that remains is a sea of lonely particles in a cold, dark, endlessly empty space. 3 scenarios, 3 different futures. Which one will happen? Based on current data, the Big Freeze is the most likely. Observations suggest that dark energy seems constant. The universe is expanding at an accelerating rate, with no sign of slowing down. There is no evidence that dark energy is growing stronger or weaker. That is why most scientists believe we are heading toward a Big Freeze. But we are not certain. Dark energy could change in the future. It might grow stronger, leading to a big rip. It might weaken, leading to a big crunch. We have only been observing the universe for a few decades. The universe itself is 13.8 billion years old. What happens over a few decades may not represent what will happen over trillions of years. So all 3 scenarios remain possible. Let us examine each one carefully. Let us understand how they unfold, when they might happen, and why. Let us face the truth about the ultimate fate of everything. Because understanding the death of the universe is also a way to understand its life. Understanding the end helps us appreciate the beginning. First, the most violent, the most terrifying scenario, the one in which everything is torn into tiny pieces. The Big Rip. The Big Rip scenario begins exactly where we are now. The universe is expanding, galaxies are drifting apart, everything still feels normal. But there is one crucial difference. Dark energy does not stay constant. It grows stronger over time. Slowly at first, almost impossible to notice. But little by little, the change becomes unmistakable. A few billion years from now, future astronomers, if any still exist, would notice something strange. Distant galaxies are not just moving away, they are moving away faster than expected. The expansion rate is no longer increasing linearly, it is accelerating exponentially. Dark energy is intensifying. Its repulsive force is beginning to overpower gravity. At first, the effects appear only on the largest scales. Distant galaxy clusters start to fall apart. Gravity is no longer strong enough to hold them together. Galaxies that once orbited each other are pushed apart. The Laniakea supercluster, our cosmic home, begins to fracture as well. Its member galaxies drift away, flung in different directions. Our local group of galaxies, including the Milky Way, Andromeda, and a few dozen smaller galaxies, still holds together. Their mutual gravity is strong enough to resist dark energy, at least for a while. But dark energy keeps growing stronger. It never pauses. It never slows down. About 60 million years before the end, the galaxies of the local group begin to separate. Andromeda, once on a collision course with the Milky Way, is now pushed away. The Triangulum galaxy recedes. Dwarf galaxies are flung outward. Each galaxy becomes isolated, alone in an ever faster expanding universe. Dark energy still does not stop. It continues to intensify. Now individual galaxies are next. About 3 months before the end, the Milky Way begins to unravel. Its spiral arms are torn away from the core. Outer stars are flung into space. A structure held together by gravity for billions of years starts to crumble. Our solar system, located in the outskirts of the galaxy, is among the first to feel the effects. The gravitational pull of the galactic center is no longer strong enough to keep us bound. The Sun and its 8 planets begin drifting outward, plunging into the dark intergalactic void. But dark energy does not stop there. 3 months is only the beginning. Its strength keeps rising at a terrifying pace. Now star systems are next. About 3 days before the end, the solar system starts to break apart. Distant planets like Neptune and Uranus are torn from their orbits. They are flung away, lost forever in darkness. Saturn and Jupiter follow. Saturn's rings shatter into countless fragments. Jupiter's moons detach from their parent planet. The Sun's gravity, strong enough to hold them in orbit for 4.5 billion years, no longer matters. Dark energy is stronger. Mars, Earth, Venus, Mercury. One by one, all are torn away. 3 days before the end, Earth breaks free from the Sun. Its orbit expands, drifting farther out. The Sun shrinks in the sky. Temperatures plummet. The oceans freeze solid. The atmosphere condenses and falls like snow. Any remaining life would perish within hours. But the death of life is only a minor detail. Dark energy continues to grow stronger. Now individual planets are next. About 3 hours before the end, Earth itself begins to fall apart. The repulsive force of dark energy overcomes the gravity holding the planet together. Continents start to separate. Mountains collapse. The crust cracks open. The Moon, which had orbited Earth for 4 billion years, is torn away as well. It shatters into fragments, scattered through space. Earth follows. Molten iron from the core erupts outward. The mantle melts. Everything that once made the blue planet beautiful is reduced to a cloud of debris. Dark energy still does not stop. Now molecules are next. About 30 minutes before the end, molecules begin to break apart. Water splits into hydrogen and oxygen. Air, nitrogen and oxygen, breaks into individual atoms. All chemical compounds dissolve. The bonds between atoms are no longer strong enough to resist dark energy. Then the atoms themselves. About 1/1,000,000th of a second before the end, atoms start to disintegrate. Electrons are ripped away from their nuclei. Hydrogen atoms, the simplest of all, 1 proton and 1 electron, are torn into separate pieces. More complex atoms like carbon, oxygen, and iron all fall apart. Finally, atomic nuclei themselves are next. The strong nuclear force, the strongest force in nature, once bound protons and neutrons tightly together. But now dark energy has become stronger even than the strong force. Nuclei shatter. Protons and neutrons fly apart. Even protons and neutrons do not remain intact. They are made of smaller particles called quarks, held together by the strong color force. But dark energy is now powerful enough to tear quarks apart as well. All structure dissolves. In the final moment, the universe becomes a sea of isolated fundamental particles. Quarks, electrons, photons, neutrinos. No structure. No bonds. Nothing more complex than a single particle. Space expands at an infinite rate. Everything is separated by infinite distances. The end of everything. When would this happen? Calculations suggest about 22 billion years from now in the most optimistic case, possibly up to 120 billion years in more conservative estimates. The exact number depends on how quickly dark energy grows stronger. Either way, it is still far away. The universe is currently 13.8 billion years old. There are at least 22 billion years left before the Big Rip, if it happens at all. A mathematician named Marcello Descanzi and his colleagues developed a new model of the Big Rip a few years ago. They realized that older models overlooked one key factor, the viscosity of the universe. Just as honey is thicker than water, the universe has its own kind of viscosity. This viscosity resists expansion. But as dark energy grows stronger, it overwhelms that viscosity. The expansion rate does not just increase, it accelerates toward infinity. This is the core idea of the Big Rip. Not merely rapid expansion, but expansion with infinite acceleration. In the final moment, the expansion speed becomes infinite and tears everything apart. The idea of cosmic viscosity is not new. It traces back to French mathematician André Lecneroix in the 1950s. He realized that spacetime is not perfectly smooth, but has an internal kind of friction. Descanzi applied this idea to dark energy, creating a new mathematical model for the Big Rip. According to this model, the Big Rip is not just a theoretical possibility, but an inevitable outcome if dark energy has certain properties. If it is a dynamic energy field that changes over time, the Big Rip becomes almost unavoidable. The question is no longer whether it happens, but when. So how likely is this scenario? Right now, not very. Observations suggest dark energy is fairly stable, with no clear signs of growing stronger. But we have only been observing for a few decades. It could be increasing extremely slowly, taking billions of years to notice. It could suddenly accelerate in the distant future, right before the end. We simply do not know. The Big Rip is the most violent scenario, a rapid ending that leaves nothing behind. But what about the opposite? What if dark energy weakens instead of strengthens? What if the universe contracts instead of expanding? In the Big Crunch scenario, dark energy does not grow stronger. Instead, it weakens, and may even disappear entirely. The outward push that keeps the universe expanding gradually fades. Gravity, the force of attraction between all matter in the universe, begins to take over. Everything that has been pushed apart for billions of years now starts to fall back together. At first, the change is almost impossible to notice. The universe is still expanding, but more and more slowly. Galaxies are still drifting away, but their retreat loses speed day by day. After billions of years, the universe reaches a standstill, the moment when expansion stops completely. Space is no longer growing, no longer shrinking. Everything hangs in a fragile balance. But this balance does not last. Gravity keeps pulling. The universe begins to contract. Galaxies stop moving away and start drifting toward one another. Slowly at first, then faster and faster. The Big Bang begins to run in reverse. Everything that was once flung outward is now returning to its point of origin. During the first billions of years, the contraction is gentle. Galaxy clusters slowly draw closer. The space between them shrinks. The cosmic microwave background, once stretched into long radio waves, now contracts into shorter, hotter wavelengths. After billions of years of cooling, the temperature of the universe begins to rise. Galaxies move ever closer. Systems that were once separated by hundreds of millions of light-years are now only tens of millions apart. Galaxy collisions, once rare, become common. The Milky Way crashes into Andromeda, not 4 billion years in the future as originally predicted, but much sooner. Other galaxies merge as well. The entire local group becomes a single colossal galaxy. But this giant galaxy does not last long. It soon collides with others from neighboring clusters. Superclusters merge together. A universe that once held hundreds of billions of separate galaxies now contains fewer galaxies, but each one is far larger, packed with trillions of stars. The temperature continues to climb. The background radiation is no longer cold microwaves, it becomes infrared, then visible light, then X-rays. The universe begins to glow. The night sky, once dark and sprinkled with stars, now blazes with radiation from every direction. Star systems start to collide. Stars from one galaxy plunge into stars from another. Most pass by without touching, because the distances between stars are vast. But some do collide, exploding as supernovae. The sky fills with brilliant bursts of light. Planets are affected too. Rising temperatures melt ice. Oceans boil. Atmospheres are stripped away by intense radiation. Life, if it still exists anywhere, cannot survive. Planetary surfaces liquefy. Eventually, even the planets themselves are pulled by gravity into nearby stars and swallowed. The universe contracts faster and faster. Galaxies no longer exist as separate entities. They merge into a single enormous, dense, blazing mass. Space shrinks until there is no empty room left. Everything is crushed together, colliding, merging. Temperatures soar to millions of degrees, then billions. Atoms are torn apart into nuclei and electrons. Nuclei themselves break into protons and neutrons. Matter returns to a seething plasma, much like the state of the universe in the first minutes after the Big Bang. The more it contracts, the hotter and denser it becomes. The universe now resembles its state 1 second after the Big Bang, then 1,000th of a second, then 1,000,000th of a second. All structure disappears. No galaxies, no stars, no planets. Only a vast, dense, scorching sea of particles containing all the mass of the universe. At last, everything collapses into a single point. A singularity. A place of infinite density, infinite temperature, infinitely curved spacetime. A place where all known laws of physics break down. The Big Crunch is complete. The universe ends in the same state it began, an unimaginably tiny point that contains everything. But is this truly the end? Some physicists suggest that after the Big Crunch could come a big bounce. When the universe contracts to its smallest size, the immense pressure might cause it to rebound, triggering a new Big Bang. A new universe is born, expands, evolves, then contracts, then bounces again. An endless cycle of birth and death, death and rebirth. In this model, our universe may not be the first. There may have been countless universes before it, each passing through a cycle of Big Bang, expansion, Big Crunch, and Big Bounce. We live in just one of these cycles. After our universe dies, a new one would be born, carrying possibly different laws of physics and an entirely new history. This idea is appealing because it removes a troubling question: what came before the Big Bang? The answer would be, a previous universe. No absolute beginning is required. The universe exists forever, through countless cycles. However, there is a problem. Each cycle increases entropy, the measure of disorder. According to the laws of thermodynamics, entropy only increases, it never decreases. After many cycles, entropy would reach a maximum. The universe could not reset to its original orderly state. This makes an infinite cycle difficult to reconcile with physics. More recently, Danish scientists have proposed another way the universe might end. They describe a phase transition, similar to water changing from liquid to vapor. The universe itself could undergo a sudden shift, changing its fundamental state. Specifically, the Higgs field, an energy field that fills all of space, might change its state. Right now, it sits in a stable condition. But there could be a lower energy state. The Higgs field might suddenly jump into this new state. When that happens, a bubble of the new state forms somewhere in the universe. This bubble expands at the speed of light, consuming everything in its path. Inside the bubble, physical constants are different. Particles have different masses. Atoms are unstable. All structures fall apart. The bubble keeps expanding until it fills the entire universe. This is another kind of apocalypse, not driven by expansion or collapse, but by a fundamental change in the nature of reality. The universe does not die, it transforms into something completely different. According to calculations, this bubble could appear at any time. Quantum fluctuations allow it to form spontaneously. The probability per second is extremely small, but not zero. It could be that right now, somewhere billions of light years away, a bubble is expanding, already on its way toward Earth. We would never know until it arrived, because it moves at the speed of light, as fast as any possible warning signal. Still, that probability is thought to be incredibly low. The universe could survive for trillions upon trillions of years before such a phase transition occurs. So this is not an immediate concern. Returning to the Big Crunch, how likely is it? Based on current data, not very. The universe is not just expanding, it is expanding faster and faster. There is no sign of slowing down. Dark energy does not appear to be weakening. Gravity is not strong enough to reverse the expansion. On top of that, the total mass of the universe, including dark matter, is not sufficient to produce the required gravitational pull. The universe has a density below the critical threshold. So the Big Crunch seems unlikely, at least according to what we know today. But we could be wrong. Dark energy might weaken in the far future. There could be hidden matter we have not yet detected. The laws of physics might change on unimaginably long time scales. We cannot be 100% certain. So the Big Crunch remains a possibility, even if a small one. So which scenario is the most likely? The one our current data points to. The one most scientists believe will happen. Not an explosion. Not a collapse. Not being torn apart. But eternal silence. Absolute darkness. Endless cold. This is the Big Freeze, the cold death, also known as heat death, the thermal death. Paradoxical, yet both names are correct. The universe will be frozen solid, and it will also die from the lack of heat. This is the most likely scenario. Not a guess, not speculation, but a conclusion drawn from observation, from data, from the most fundamental laws of physics. The second law of thermodynamics says that in a closed system, entropy always increases. Entropy is a measure of disorder, of chaos. Everything that is ordered slowly becomes disordered. Concentrated energy spreads out, thins away. Heat flows from hot regions to cold ones until everything reaches the same temperature. The universe is a closed system, the largest one possible. There is nothing outside it to exchange energy with. So the entropy of the universe always increases. Relentlessly, irreversibly. With every passing second, the universe becomes just a little more disordered. Every star that shines, every planet that spins, every thought in your brain, all of it increases entropy. Eventually, given enough time, entropy reaches its maximum. It cannot increase any further. At that point, all energy in the universe is evenly distributed. There are no hot places and no cold places. No concentrated energy. No ability to do work. No capacity for change. The universe reaches thermodynamic equilibrium. This is heat death. Here is what the timeline looks like. Right now, the universe is 13.8 billion years old. The Sun has about 5 billion years left to live. Smaller stars live longer, up to 10 trillion years. But in the end, all of them run out of fuel. Around 100 trillion years from now, every star in the universe will have gone dark. 100 trillion years, written out as 10 to the power of 14 years, a number thousands of times larger than the current age of the universe. Yet compared to eternity, it is only a blink. When the last star goes out, the universe falls into darkness. No new starlight is ever born. Only remnants remain, white dwarfs, neutron stars, black holes. These objects do not shine, or shine only faintly. The universe becomes a stellar graveyard. Planets continue to orbit the corpses of their parent stars for a while. But over time, gravitational disturbances push them out of stable orbits. Some fall into white dwarfs or neutron stars and are swallowed. Others are flung into space, becoming rogue planets, cold, dark, and alone forever. Galaxies are affected too. Over trillions of years, stars inside galaxies interact and exchange energy. Some fall into the central black hole. Others are ejected at high speeds, escaping the galaxy entirely. Slowly, the galaxy evaporates, leaving behind only the central black hole with a few stellar remnants nearby. Around 10 to the power of 40 years from now, even black holes begin to die. Stephen Hawking discovered that black holes are not completely black. They emit radiation from their boundaries, known as Hawking radiation. It is incredibly weak, almost impossible to detect. But over time, this radiation causes black holes to lose mass, shrink, and eventually evaporate completely. Small black holes evaporate quickly. Large black holes evaporate slowly. Supermassive black holes at the centers of galaxies, billions of times more massive than the Sun, take 10 to the power of 100 years to fully evaporate. This number is almost impossible to imagine. It is 1 followed by 100 zeros. larger than the number of atoms in the observable universe. When the last black hole evaporates, there is almost nothing left. Only isolated particles scattered through space. Photons, electrons, neutrinos, positrons. They are separated by millions of trillions of light years. The chance that any two particles ever meet is essentially zero. Each particle is alone in the vast universe. The temperature of the universe drops close to absolute zero, -273 degrees Celsius. Not exactly zero, because the third law of thermodynamics says absolute zero can never be reached. But unimaginably close. The difference is meaningless. Space continues to expand. Dark energy keeps pushing. Particles drift farther and farther apart. The density of the universe drops to nearly zero. On average, there is less than one particle in a volume larger than a present-day galaxy. The cosmic microwave background, once warm after the Big Bang, has stretched so much that it can no longer be detected. Its wavelength spans billions of light years. Its energy is almost zero. Its temperature is almost absolute zero. The universe reaches thermodynamic equilibrium. Every region has the same temperature. No gradients, no differences. Energy is evenly spread and cannot be used to do work. Entropy is at its maximum. It cannot increase further. In this state, time loses its meaning. Time only matters when things change. When events happen. But in a heat-death universe, nothing changes. Nothing happens. Everything is perfectly still. 1 second and 1 billion years are indistinguishable. Time becomes a meaningless concept. No life can survive. Life requires energy, requires temperature gradients to function. In a heat-death universe, there is no usable energy. Nothing to eat. Nothing to burn. No way to maintain order. All complex structures fall apart. No consciousness remains. No observers. No one left to know that the universe has died. Only lone particles drifting through infinite space, cold, dark, and silent. This is heat death. Not a dramatic ending with a massive explosion or a violent collapse. But a slow fading, a gradual extinguishing. The universe does not die in glory. It dies in silence. Not with a bang, but with a final sigh. This scenario is based on the most solid physics we have. The laws of thermodynamics have been tested countless times. They have never been violated. If they are correct, heat death is unavoidable. It is only a matter of time. Of course, time here means 10 to the power of 100 years or more. Humanity, if it still exists, would be unrecognizable. Earth would have died long ago. The sun would be gone. The Milky Way would have dissolved. Everything we know would have vanished hundreds of trillions of years earlier. So heat death is not an immediate concern. It is so far away that it is hard to even imagine. But it reminds us that nothing lasts forever. Everything has an end. Even the universe itself. This may sound sad. Everything we build, everything we love, everything we value eventually disappears. But there is also beauty in it. We live in a rare moment when the universe is alive, complex, and full of energy. We are part of this miracle, even if only for a brief instant compared to eternity. But perhaps this is not the true end. Perhaps there is something beyond heat death. In a heat-death universe, everything seems to have come to an end. No more stars, no more planets, no more life. Only lonely particles drifting through cold, dark space. Entropy has reached its maximum. Time itself loses meaning. But maybe the story does not end there. Quantum mechanics teaches us one thing: fluctuations never truly stop. Even in a perfect vacuum, even at temperatures close to absolute zero, space itself still trembles. Pairs of matter and antimatter particles continue to pop into existence and vanish in an instant. Energy keeps fluctuating up and down, obeying Heisenberg's uncertainty principle. In a heat-death universe, these fluctuations still go on. They are incredibly tiny, incredibly rare, but they still happen. If you wait long enough that the number of years stretches beyond imagination, perhaps a very special fluctuation occurs. One large enough to create energy, to generate matter, to ignite a brand new Big Bang. The probability of this is unimaginably small. Far smaller than winning the lottery millions of times in a row. But it is not zero. Given infinite time, anything with a non-zero probability will eventually happen. Wait long enough, and a new universe could spontaneously arise from the quantum void. This new universe would experience its own Big Bang, its own expansion, its own galaxies. It might have different physical laws. Different constants. It could be completely unlike the old universe. This would be a form of cosmic rebirth, not through a big bounce, but through random quantum fluctuations. Physicist Roger Penrose, a Nobel Prize winner, has proposed a different idea. He calls it conformal cyclic cosmology. In his view, when the universe reaches heat death, entropy is maximal and time loses its meaning. When time loses meaning, the distinction between before and after dissolves. The universe can effectively reset and begin again. This idea rests on deep and complex mathematics involving conformal geometry. Penrose argues that the final state of a universe, when everything has dispersed into individual particles, is mathematically similar to the initial state of a new universe. There is no absolute scale of size. No absolute clock. The end of one universe can be the beginning of the next. In this model, the universe goes through infinite cycles. Each cycle is called an aeon. We live in one aeon. Before us, there were countless others. After us, there will be countless more. Each aeon begins with a Big Bang, ends with heat death, and then smoothly transitions into the Big Bang of the next aeon. Penrose has even searched for evidence of this model in the cosmic microwave background. He looks for concentric circles that might be the traces of supermassive black hole collisions from a previous aeon. Some researchers think they have found such circles. Others argue they are nothing more than random noise. The debate continues. Another way to think about the end is to realize that in heat death, when entropy is maximal, all microscopic states are equally probable. No configuration is favored over another. The universe can occupy any arrangement with equal likelihood. Most of these configurations are chaotic and uninteresting. But a tiny fraction, extraordinarily rare, are ordered. They have structure. Given enough time and enough space, an ordered configuration will eventually appear by chance. It could be a galaxy. It could be a star. It could even be a fully formed brain with memories, emerging from random fluctuations. This hypothetical brain is known as a Boltzmann brain, named after physicist Ludwig Boltzmann. It presents a strange paradox. In a heat-death universe, the probability of a single brain appearing is far higher than the probability of an entire orderly universe appearing, simply because a brain is much smaller and requires less order. This leads to an unsettling question. How do we know we are not Boltzmann brains? How do we know our memories of the past, of Earth, of the universe, are not just random illusions created at the moment our brains formed? Most physicists believe we are not Boltzmann brains, but proving that turns out to be harder than it sounds. So we return to the question of what comes after the end. The honest answer is that we do not know for sure. Heat death may be the absolute end. The universe reaches equilibrium and stays there forever, unchanged and unevolving. The distances between particles grow without limit. Temperatures drop towards zero. Everything freezes into a final state. Or there may be something we do not yet understand. The laws of physics might change on extremely long timescales. Dark energy could evolve after hundreds of trillions of years. There might be a mechanism that allows the universe to be reborn. We have only observed 13.8 billion years. What happens after 10 to the power of 100 years could be completely different. Some physicists believe information is never truly lost. Even when black holes evaporate, information is preserved in some form. Even in heat death, information about the previous universe may remain, encoded in tiny correlations between particles. From that information, a new universe might one day be reconstructed. Or perhaps in a multiverse, when one universe dies, countless others are still being born. We worry about the death of our universe, but in the larger picture, it may be just one bubble in an eternal sea of inflation. This bubble fades, another forms. The whole process continues forever. What we can say with confidence is that we do not know everything. Every prediction about the distant future is based on extrapolating the laws of physics we know today. But those laws may not apply forever. There could be new phenomena, new forces, new dimensions we have yet to discover. The universe has surprised us many times before. We once thought Earth was the center of everything, and it was not. We thought the universe was static, and it turned out to be expanding. We thought that expansion was slowing down, and it turned out to be accelerating. Each time, reality proved stranger than our imagination. So when we talk about the end of the universe, we must remain humble. The Big Freeze appears to be the most likely outcome based on what we know now. But what we know now could be wrong. There may be far more we have yet to learn. The end may not be an ending at all, but a transition, a transformation into something new. One thing is certain. The universe has existed for 13.8 billion years. It will exist for at least trillions more, perhaps millions of trillions, perhaps forever. In that vast span of time, countless wonders will unfold. Countless stars will be born and die. Countless civilizations may rise and fall. Countless discoveries, countless creations, countless marvels. We are fortunate to live in a golden age of the universe. A time when stars still shine, galaxies are still beautiful, and life can still exist. A time when the universe is old enough for complexity, yet young enough to still have energy. This is a precious gift. So what have we learned from this long cosmic journey? We have come a long way. From the moment before the Big Bang, when time did not yet exist, when space itself had no meaning. We looked into the singularity, a place where all the laws of physics break down, where everything began from a point smaller than an atom. We watched the universe explode outward in a moment of wild inflation, expanding faster than light by millions upon millions of times. We saw energy turn into matter, matter gather into stars, stars gather into galaxies. From almost nothing, the universe created itself. We explored the 95% of the universe that is invisible. Dark matter holds galaxies together, even though we do not know what it is. Dark energy pushes the universe to expand faster and faster, even though we do not understand its nature. These two mysteries make up most of the cosmos, and they remain unsolved puzzles. We counted 200 billion galaxies scattered across space. Each galaxy contains hundreds of billions of stars. Each star may have planets. Each planet may host life. The numbers are almost impossible to grasp, but they suggest something profound, that we may not be alone. We asked about boundaries. Does the universe have an edge? What lies beyond it? Are there higher dimensions? Could it be possible to travel between universes? These questions push the limits of understanding and bring us to the very edge of what science can answer. In the end, we looked far into the future. 3 possible endings: the Big Rip, tearing everything apart, the Big Crunch, collapsing everything back into a singularity, and the Big Freeze, fading into eternal silence and cold. Each scenario is grounded in physics, each one is possible, but the Big Freeze appears to be the most likely fate. 20 questions. 2 hours of exploration. From birth to death. From the smallest to the largest. From the distant past to the infinite future. We have traveled through it all. So what did we learn? The first thing is that what we know is extraordinary. Just a few hundred years ago, humans believed Earth was the center of the universe, that the sun revolved around us, that the stars were tiny lights painted on the sky. Today, we know Earth is just a small planet orbiting an ordinary star, in the outskirts of an ordinary galaxy, among hundreds of billions of others. We know the universe is 13.8 billion years old. We know it was born from the Big Bang. We know it is expanding. We know its composition: 5% ordinary matter, 25% dark matter, 70% dark energy. We have measured its size, its temperature, and its expansion rate with astonishing precision. We discovered the cosmic microwave background, the faint afterglow of the Big Bang. We found thousands of planets beyond our solar system. We captured images of black holes. We detected gravitational waves. With every decade, we learn more, understand more deeply, and see farther than ever before. But the second lesson, the more important one, is that what we do not know is far greater still. Every answer opens the door to hundreds of new questions. We know dark matter exists, but we do not know what it is. We know dark energy drives cosmic expansion, but we do not understand its true nature. We know the universe began with the Big Bang, but we do not know what triggered it. We do not know how life began. We do not know whether anyone else is out there. We do not know if higher dimensions exist. We do not know for certain how the universe will end. Every field we study reveals more mysteries than it resolves. Maybe that is the beauty of science. Not having all the answers, but never stopping the questions. Not reaching a final destination, but embracing the journey of discovery. Each generation of scientists stands on the shoulders of those before them, seeing a little farther and understanding a little more. We are tiny specks of dust on a small rock, racing through space at 800,000 kilometers per hour. We live on a minuscule planet, orbiting a small star, in an average galaxy among hundreds of billions of others. In physical terms, we are insignificant. We occupy a negligible fraction of space and a fleeting moment in time. And yet, we are conscious. We can think, learn, and understand. We are trying to comprehend a universe 93 billion light-years across. The miracle is that we are succeeding. Despite our smallness, despite our brief existence compared to eternity, we have unraveled some of nature's greatest secrets. We know how the universe began. We know what it is made of. We have an idea of where it is heading. Not perfectly, not in every detail, but we see the big picture. That is an astonishing achievement for a species that has practiced science for only a few hundred years. Remember that we are made of star dust. The elements in your body were forged in the hearts of earlier generations of stars. The carbon in your DNA, the calcium in your bones, the iron in your blood, all of it came from stars. You do not just live in the universe. You are a part of it. You are one way the universe becomes aware of itself. Carl Sagan once said, "We are a way for the universe to know itself." A simple sentence, but a profound one. For billions of years, the universe existed without awareness. Stars were born and died, galaxies collided, planets formed, all without anyone to observe or understand. Then, somewhere, on a small planet orbiting an ordinary star, life emerged. Life evolved into consciousness. Consciousness began to ask questions. Now the universe can look back at itself through our eyes. It can think about its origins through our minds. It can wonder about its fate through our awareness. We are small, but we are special. We are the part of the universe that has awakened. The journey of discovery continues. There are still countless unanswered questions and unresolved mysteries. Future generations will know more than we do. They will have more powerful telescopes, faster computers, and deeper theories. Maybe they will discover dark matter. Maybe they will understand dark energy. Maybe they will find life beyond Earth. Or maybe they will discover that what we believe today is wrong. Maybe they will replace the Big Bang with a better theory. Maybe they will uncover higher dimensions, a multiverse, or something we have not even imagined yet. Science constantly corrects itself, constantly evolves, and always moves forward. So thank you for taking this journey. Thank you for spending 2 hours exploring the greatest mysteries of the universe. Thank you for being curious, for asking questions, for wanting to understand. That is the spirit of science. That is what makes us human. Never stop asking questions. Never stop searching for answers. The universe is vast, beautiful, and full of mystery. Every day we learn a little more. Every generation understands a little deeper. That is the greatest gift science gives us, the ability to understand the world around us, our place in the cosmos, and our origins and destiny. One day, we will return to the stars. Not in a mythological sense, but literally. When we die, the elements in our bodies return to the earth. The earth itself will one day die, swallowed by the sun. The sun will die too, scattering its elements into space. Those elements will become part of new clouds of gas, new stars, new planets, and perhaps new life. We were once star dust. We will become star dust again. That is the eternal cycle of the universe. We are part of it. We are it. The universe is not a distant place, it is our home, our origin, and our future. So tonight, look up at the sky. Look at the stars shining above you. Remember that every star is a sun. Every sun may have planets. Every planet may have life. We are not alone in this vast universe. At the very least, we have each other. We have the ability to wonder, to explore, and to understand. That is the gift. That is the miracle. And that is why we never stop searching for answers to the biggest questions about the universe.